Hello, my dear students. I hope you all are really doing great. First of all, I welcome you all on this amazing platform of PhysicsWallah English channel. Students, now we have moved to lecture number 7. And in the 7th lecture of chemistry, we'll be talking about a very important compound referred as carbonyl compounds. Highly important for all the competitive exams. Students, before moving ahead, let's discuss the thing which we are going to do today. First, we'll be talking about Gmp of Carbonyl, Gmp, general method of preparation of carbonyl compounds. Carbonyl compounds, it's nothing but aldehydes and ketones. So we'll be talking about the general method of preparation of both aldehydes and ketones. Next, we'll move to chemical reaction. In the chemical reaction, first we'll be starting with nucleophilic addition reaction. And in this nucleophilic addition reaction, we'll be doing addition reactions of lot of compounds. Addition reaction. We'll be talking about the addition of alcohol. We'll be talking about the addition of alcohol, ROH, addition of water, addition of CN minus. Then we'll be talking about addition of per acid, that is Beers-Willigers reaction. Okay, then we'll be talking about addition of ammonia derivative to form imines. So addition of NH2Z species, right? Then we'll be talking about Wolff-Kishner reduction. Then we'll be talking about Clementine reduction. WKR stands for Wolff-Kishner reduction. Then we'll be talking about Clementine reduction. Then some important reactions like aldol. In aldol also we'll be doing lot of different types of aldol reaction. Aldol, cross aldol, intramolecular aldol. Then we'll be talking about Cannizzaro reactions. Once again, Cannizzaro, cross Cannizzaro, intramolecular Cannizzaro. Then we're talking about Wittig reaction. Then haloform reaction. Then we'll be talking about tolerance test. So in this particular lecture, our main focus will be on these particular topics only. So now, without wasting any further time, let's start our today's session. Student, if I talk about carbonyl compounds, it's nothing but aldehydes or ketone. If it's having a general structure like this, it's referred as aldehyde. Aldehyde. On the carbonylic carbon, this particular carbon is referred as carbonylic carbon. On to this carbonylic carbon, if on one side I am having alkyl group, on other side I am having hydrogen, then it is aldehyde. If to this carbonylic carbon, on both the sides I am having alkyl group, then it is ketone. Right? These things you understand. Student, if I talk about the structure of this particular carbonyl, C double bond ORH. Student, first, this particular C double bond O is highly polar. It can be written like this, C plus O minus, electromatic effect, right? Highly polar. Or we can say it's more polar as compared to C double bond C. Because of this polarity, this carbonyl compound always undergo nucleophilic addition reaction. A nucleophile always prefers to attack on this carbonylic carbon, whereas alkene, being less polar, it mainly is undergo electrophilic addition reaction. We have studied that, right? Alkene prefers EAR, whereas carbonyl prefers nucleophilic addition reaction, NAR. Nucleophilic addition reaction. If I talk about the geometry, hybridization is sp2. So bond angle 120, geometry planar, right? Now, if I talk about the reactivity Which one will be more reactive? Students, in general, aldehydes are more reactive as compared to ketone. Why aldehydes are more reactive as compared to ketone? We'll discuss about this particular point in more detailed way in this particular lecture only. Okay, so students, now let's move towards the general method of preparation of carbonyl compounds. And now let us discuss the general method of preparation of carbonyl compound. So now we are going to discuss a few important methods through which we can synthesize either aldehydes or ketone. Let us discuss all these methods one by one. The first method, it's all about hydration of alkyne. So I am going to generate carbonyl compound from alkyne. Okay, and this reaction is like this: alkyne treated with acidified water generates carbonyl compound. It can be aldehyde, it can be ketone. Let's see in which case I will get ketone and in which case I will get aldehyde. Okay, student, if I write any general alkyne, it will have a general formula RC triple bond CH. Now it's treated with acidified water. I can take H2SO4 in the presence of HgSO4, right? We have done this reaction. Or I can take simple H plus slash H2O, right? Acidified water. Let's see. Can I say this reaction always occurs via carbocation method? First, I will have the formation of a more stable carbocation. Then on this more stable carbocation, the nucleophilic part will attack. The nucleophile is water here. So first I will have the formation of carbocation, and now this hydrogen will simply attack on this carbon. So I will have carbocation getting formed on this carbon. On this carbon, the nucleophile water will attack, and I will have the formation of alcohol, right? So I'm going to break one double bond. I'll add one hydrogen here. I'm going to, already one hydrogen was there. One more hydrogen I have added, and here I will add alcohol. Student, if I look at this particular product, it's nothing but enol, alkene plus alcohol, right? Now it will readily undergo tautomerization because in case of monocarbonyl compound, the keto form is more stable as compared to the enol form. Now I am going to form a compound like this, right, student? So if I do the hydration of alkyne, I am going to get ketone. So students, now my question to you is whether we will get ketone only in all the cases, or can we get even aldehyde also? Can you tell me one case where if we do the acidic hydrolysis of alkyne, I am going to get aldehyde as my final product? Can you tell me? Yes, there is only one case, and that's nothing but the hydrolysis of acetylene. That's nothing but ethyne. So if I do the hydrolysis of acetylene, HC triple bond CH, if I treat it with dilute H2SO4 in the presence of HgSO4, or I can take H plus slash water, right? Once again I will have electrophilic addition reaction. H plus will get added to one carbon, OH will get added to other carbon. I will have the formation of HC double bond C, OH, H and H. It will readily undergo tautomerization, and my final product is going to be HC double bond O CH3. So here my final product is aldehydes. So if I do acidic hydrolysis of ethyne, that is nothing but acetylene, in that particular case will get aldehyde as my final product. Rest in all the cases I will get ketone as my final product. Am I clear, students? Let's do 1 to 2 questions in order to understand this concept in a better way. I'm having one alkene, and this alkene is treated with H plus in the presence of H2O. Basically, I am doing acidified hydrolysis, right? Perfect. Symmetrical alkenes. So what I will do, I will break this bond, will add one H on one carbon and OH on the other carbon. So my product, first I will get this one, COH doubly bonded CH3, and now it will readily undergo tautomerization and I will have CH3 C double bond O CH2 CH3, right? 1 2 3 4 butane 2 on as my final product. I hope I am crystal clear with this particular question, right? Is it clear, everyone? Let's move to the next question. Now student, if we look at this particular question, now it's treated with H+. I am going to do the electrophilic addition reaction. Reaction of pi bond with H+ generates carbocation. Now on which carbon I am going to generate carbocation? On that carbon which is giving me a more stable carbocation, right? Now which carbon will give me a more stable carbocation? Carbon number 1 or carbon number 2? Which one? Can I say carbon number 2? Why? Stabilized by resonance in conjugation with ring. So here I will have the addition of H+. Here I will have my carbocation on which the nucleophile will attack, and I will have the formation of PH, C doubly bond C OH, right? H and CH3 will undergo tautomerization and I will have PH C double bond O CH2 CH3 as my final product. Am I clear, students? Please copy it. Now let us move ahead. Students, moving to the next method which we are going to discuss for the synthesis of carbonyl compound is reductive ozonolysis of alkene. Let's try to understand this. Alkene. So it will have a general formula C double bond C R. I can take H over here, R dash and one more R double dash. It's also alkene only, right? Now it's treated with ozone but in reductive medium. Now what do we mean by reductive ozonolysis? Student, in the arrow if you find O3 and below if you find any one of these, Zn plus H2O2, Zn plus H2O, Zn plus CH3 twice S, or even H2O2 plus CH3 twice S. In all cases, you are going to do reductive ozonolysis. Now, what we will do in reductive ozonolysis, I am giving you a very simple trick. Simple. You break this C double bond C. Now, add oxygen to each doubly bonded carbon. Okay, so I am going to add one oxygen over here, one oxygen over here. Now, can you tell me what is the covalency of oxygen? It's 2. So, can I say this carbon will get connected to oxygen via a double bond, and this carbon will also get connected to oxygen via a double bond, right? So, the product which I am going to get here is R C double bond OH plus C double bond O R dash and R double dash. These are the two products which I am going to get here. One aldehyde and the second one is ketone. Right, students? I hope you understood this reductive ozonolysis. Please do copy it. Have you copied these things? So shall we move ahead? Okay. Now we have to do reductive ozonolysis of these compounds. Zn in the presence of H2O, reductive ozonolysis. So what will be my product here? I am going to cleave this double bond here also and here also, right? Perfect. Let's number it. It will be easier for us. 1, 2, 3, 4, 5 and 6. Now carbon 4 and 5 was connected via a double bond, right student? 1 and 6 was also connected via a double bond. But between 5 and 6, I was not having a double bond. So I'm going to draw this 5 and 6. On carbon number 5, I am having a methyl group. On this carbon number 5, I was having a double bond, right? So I will add one doubly bonded oxygen over here. On carbon number 6, only hydrogen is there and this double bond is also there. So I'm going to add one double bond over here and hydrogen over here, right? This is one of my product. Can I say I will have the same repetition of product? Now I am going to draw 1, 2. This is my 1, 2, right? Now on carbon number 1, I was having a methyl group. On carbon number 1 itself, I was having a double bond also. So I will add one doubly bonded oxygen over here. On carbon number 2, one more double bond. So I will add one double bond hydrogen over here. So this 1, 2 is also done. Now 3, 4, same repetition. Same story, right? What we get in the Bollywood movies. 3, 4, now we'll have double bond O, H, and then here I will have a doubly bonded oxygen over here. So can I say I'm getting 3 moles of the same product, right students? I hope you understood this reductive ozonylasis of this particular compound. Now can you do this for this one? It's very easy, right? We have done the complex one. Now you can do this one very easily. Simply cleave this, add one doubly bonded oxygen over here and one doubly bonded oxygen over here. So you will have Me C double bond O, Me plus Me C double bond O H. So I'm getting both aldehyde as well as ketone through this reductive ozonylasis. Right students? I hope you understood both these questions. Please copy it. Now, shall we move ahead students? Okay. Now we are going to study about oxidation of alcohol. Student, if we do the oxidation of alcohol, we can get carbonyl compounds. But here, it simply depends on which type of oxidizing agent I am going to take and what's the nature of alcohol. Whether it is a 1 degree alcohol, 2 degree alcohol or a tertiary alcohol. In the last lecture only we have studied these things, right? Even I had given you the list of mild oxidizer, strong oxidizer. If I'm having a primary alcohol, if this primary alcohol is treated with a mild oxidizer, have I told you aldehyde is going to be my final product? Primary alcohol treated with a strong oxidizer, acid is the final product. Secondary alcohol treated with mild as well as a strong oxidizer, ketone is the final product. Tertiary alcohol, no replaceable hydrogen, will not undergo oxidation easily. Right student? Let me write that here also. I'm having a primary alcohol RCH2OH. It's treated with a strong oxidizer. What I will get? Oxidizer. RCH2C double bond OOH. Can you tell me one strong oxidizing agent? Yeah. Alkaline KMNO4. Acidified sodium dichromate solution. Right? Primary alcohol treated with a mild oxidizer. What will be my final product? Aldehyde. RC double bond OH. So student, we can generate aldehydes from primary alcohol if I treat primary alcohol with a mild oxidizer. Right? Can you tell me a few mild oxidizer? Yeah. John's reagent, Collins reagent, PCC, PDC, X2 in the presence of OH minus, right? All these are the mild oxidizer. Now, I'm having a secondary alcohol, R, C, R dash, H, OH. Is it a secondary alcohol? Definitely yes. Treated with either mild or strong oxidizer. in both the case, my final product is going to be RC double bond O R dash. So secondary alcohol on oxidation will always generate ketone, whereas primary alcohol on oxidation may generate aldehyde or acid depending on the nature of oxidizing agent. Am I clear? Please copy it. Student, now let's do some question related to oxidation of alcohol. We have studied about this reagent also in the last class only, MnO2, selective reagent used for the oxidation of allylic alcohol and benzylic alcohol, right? Allylic and benzylic. Okay, here students, here there is no benzene ring, so we don't need to bother about benzylic alcohol. But now we need to check whether I am having allylic position or not. Let's see. I am having double bond. So can I say this carbon is going to be allylic carbon? Allylic. This one is also allylic. Perfect. This one is also allylic. Right? So these three positions are basically the allylic position. Now I need to check which allylic alcohol is going to get oxidized. Students, no doubt this is allylic alcohol. But is it a 3-degree alcohol? Definitely yes. Will it get oxidized? No. Whether it is a mild oxidizer or a strong oxidizer, a 3-degree alcohol, even though it is a allylic alcohol, but still it will not get oxidized because it does not have any replaceable hydrogen. This one will remain as it is. Is it allylic alcohol? Not at all. Simple primary alcohol. Will it get oxidized by MnO2? No. MnO2 only oxidizes allylic and benzylic alcohol, that too 1 degree or 2 degree. Now this one, is this the allylic carbon containing alcohol? So allylic alcohol, primary allylic alcohol will definitely get oxidized. So if I write the product, my final product is going to be double bond. This one will remain as it is because this alcohol was a 3-degree alcohol, 3 degree. Now this one will get oxidized and hydrogen over here. Now here I will have one pi bond and this one will remain as it is. So only this particular alcohol was getting oxidized if I treat this substrate with MnO2. I hope you understood this one. Let's do the second part. I'm having alcohol, right? It's a polyhydric alcohol. More than one alcoholic group is present, OH, OH, OH. This one, primary alcohol, will definitely get oxidized by hot alkaline KMnO4, strong oxidizing agent, right? Strong oxidizing agent. It will definitely get oxidized. So from here I will have carboxylic acid. Secondary alcohol, this one will also get oxidized. 2-degree alcohol, this one 3-degree alcohol will remain as it is, won't get oxidized. So shall I write the final product? Let me write that. 6-member ring. Then I will have C double bond O, OH over here. This one will get oxidized to ketone and this one will remain as it is. Please copy it. So let's move ahead, student. Now let's generate carbonyl compound from salt of carboxylic acid. And right now we are going to study about dry distillation of calcium salt of acid. I'm having an acid RC double bond OOH. And now it's treated with CaOH whole twice. Can I say I will have simply acid-base reaction? Right? H plus getting released from here, OH minus getting released from here. And I will have the formation of calcium salt of fatty acids having the molecular formula RC double bond O, O minus whole twice Ca2 plus. This is referred as calcium salt of acid. Am I clear, students? Now, if I heat it strongly, if I do the dry distillation of this RC double bond O twice Ca, if I heat it strongly, the product which I am going to get is this one. Very important one. Just, I am giving you a trick. Just place this R as it is. Put this C double bond O as it is. Now, just move to the left side of this carbonyl. You are having one alkyl group. Put one more alkyl group over here. Remove CO3 from here. CO3 from here and Ca. So you will have final product as CaCO3, which may decompose as CaO plus CO2. So what you are getting? You are getting, students, ketone as your final product. You are getting ketone as your final product. How? Let's see once again. Let us suppose I am having CH3, C double bond O twice Ca. If I heat it strongly, what I am going to do? First, I will write this one CH3 as it is. I will keep this C double bond O as it is. I will again move to the left side of the carbonylic carbon, CH3. This is my final product. I will remove CO3 from here. Ca plus CO3, CaCO3 may on decomposition may give CaO plus CO2. Right? So this is how we generate ketone by doing dry distillation of calcium salt of fatty acids. Please do copy it. Okay. Can you do it? Very easy. Easily you can do it, students. You are having ethyl group. Just copy this. Ethyl, Et. Write Et. C double bond O. Keep as it is. C double bond O. Again repeat this. CET plus CaCO3. Same. pH. Left side of the C double bond O. pH. Keep this pH as it is. C double bond O. Okay. Once again move to the left side of C double bond O. You are having pH only. pH. Am I clear? Okay. Let's do one more question. Friend, now the question which is there on the screen. Here basically we are having two different salt of fatty acids. Right? One calcium salt of acetic acid. Let's name it as A. And the other one is calcium salt of formic acid. And now I am doing the dry distillation of both these salts. How many products we are going to get? Student, here basically we will get three different products. One, through this one, if I do the dry distillation of this only, the product which I will get is CH3, C double bond O, CH3. Right? One, if I do the dry distillation of this only, calcium salt of formic acid, the product which I am going to get is this one. And one, we can have cross product also, right? Dry distillation of both these products. So what will be my cross product? CH3, C double bond O from one salt and H from the other salt. So how many products you have got? Three products. Right, students? So this particular reaction is nothing but the cross reaction. I hope you understood this one also. Let's move ahead. On passing vapor of fatty acids over manganese oxide at 300 degrees centigrade. Now this particular question is also related to the previous concept itself. I am having RC double bond OOH. And if this carboxylic acid is passed over, or if the vapor of this carboxylic acid, vapors of this carboxylic acid is passed over MnO at 300 degrees centigrade, once again I will have the formation of ketone. RC double bond O. Student, here also we can have mixture of products if I'm having a vapor of Let's suppose RC double bond OH plus HC double bond OH. And now if the vapor of these two acids is passed over MnO over 300 degrees centigrade temperature, here I will have mixture of product. I will have RC double bond OR as one of my product, then I can have HC double bond OH as one of the product, and then we can have RC double bond OH as also one of the product. So here also, just like the dry distillation of calcium salt of fatty acids, the reaction is same, the concept is same. Here we simply do one thing, we pass the vapor of acid over MnO at 300 degrees centigrade. Am I clear, students? So shall we move ahead? Let's move ahead. Students, now let's move to the next method through which we can synthesize carbonyl compound. And here we are going to synthesize carbonyl compound from alkyl halides by doing the hydrolysis of geminal dihalide. Can you tell me what do we mean by the term geminal dihalide? Geminal dihalide. If a carbon is having two halogens, such system, carbon containing two halogens or two halogens attached on the same carbon is referred as geminal carbon. Such a system is geminal dihalide system. Now, let's take one example. I am having R, CH2, CH, X and X. And now if I will do the hydrolysis, let's treat it with aqueous KOH. I will have substitution reaction, right, students? And can I write my product as RCH2CHOH? Simply this halogen will get replaced by X getting replaced by OH minus, X getting replaced by OH minus. So I will have now geminal hydroxyl system. Such a system is highly unstable. Why? Because here I will have intramolecular hydrogen bonding. Now you will say, sir, intramolecular hydrogen bonding is a stabilizing factor. It supports instability. Then why the stability will be less here? Student, here because of intramolecular hydrogen bonding, I will have 4-member ring formation, right? Let's see how we are having this 4-member ring formation. 1, 2, 3 and 4. And this 4-member cyclic ring is highly unstable ring. Highly unstable ring. So because of this 4-member chelation, the stability of geminal hydroxyl system is very less and it readily loses 1 mole of water. I will remove 1 mole of water from here. Simply you can do one thing, remove OH from here, H from here, and then write the product. So we'll have CH2, CH, oxygen, covalency 2, so this one, and here I will have R. So what is your final product? Aldehyde here. R, CH2, C double bond O, H. So students, if I am having a geminal dihalide system, if it's treated with or if it undergo hydrolysis, if I treat a geminal dihalide by water, aqueous KOH, in that particular case it will readily undergo hydrolysis. I will have the formation of geminal hydroxyl system. This system is a geminal hydroxyl system, highly unstable system, readily undergo dehydration, will lose 1 mole of water to form a carbonyl compounds. Am I clear? Please copy it. Now, let's do 1 or 2 questions related to this one. I'm having alkyne. This alkyne is treated with HX, 2 moles. We have studied this reaction. Alkyne on reaction with HX. First, I will have the formation of vinylic halide, right? Again, it will undergo addition and I will have the formation of geminal dihalide. The reaction will occur via Markovnikov addition. So the nucleophilic part will get added to the more substituted carbon. Can I say this carbon is the more substituted carbon? So after adding 2 moles of HCl, Can I say my product will be, product A will be CH3C Cl Cl. I have added 2 moles of nucleophile. The nucleophilic part is Cl minus here, and here I will have CH. Already one hydrogen is there, and now I am adding 2 hydrogens, so CH3. Now it's treated with aqueous KOH. I will have geminal hydroxyl system, OH. Cl getting replaced by OH. Cl getting replaced by OH. Geminal hydroxyl system, highly unstable. I will remove one water molecule, and my final product will be CH3 C double bond O CH3. Right? So B is propanol. The next one. Student, I am having alkene. It's treated with NBS. N-bromosuccinamide. What this will do? Source of Br dot. This Br dot will do allylic substitution here. So I will have A as my product. A is this one. Now it's treated with H2O. So the product B will be allylic alcohol. Now it's treated with PCC, mild oxidizer, 2-degree alcohol, will undergo oxidation, and I will have the formation of this one. Right? So the final product C is this one. B is this one. A is this one. A, B, and C. I hope this question is also clear to you all. Please copy it. Students, now let's move to the next method through which we can synthesize aldehyde or ketone, or the next method which is there on your screen. This particular process is referred as Wacker process. It's also one of the methods through which we can synthesize aldehydes or ketone. If I talk about this particular reaction, it's nothing but oxidation reaction. Here we are going to do oxidation of alkene. Okay, how does this reaction occur? Let's try to understand. I'm having an alkene RCH doubly bonded CH2. Any alkene with this general formula. Now it's treated with PdCl2. I'm going to take catalytic amount of CuCl2 in the presence of air. When this alkene is treated with PdCl2 containing catalytic or a small amount of CuCl2 in the presence of air, alkene gets oxidized, and my final product is going to be R C double bond O CH3. This addition of oxygen will always occur on more substituted carbon. Addition of oxygen will occur on more substituted carbon. Since this carbon was more substituted, so oxygen will get added to that particular carbon. Now your question is, sir, here we are getting ketone. Are we going to get ketone always only? My answer is no. If I am having ethene as my substrate, CH2 doubly bonded CH2, and now if it's treated with PdCl2 in the presence of CuCl2 O2, my final product is going to be CH3 C double bond OH. Rest in all other higher alkenes, I am going to get ketone. If ethene is there as a substrate, in that particular case, we will get aldehyde. Am I clear, students? Here in this particular reaction, right now the oxidation state of Pd is +2. This Pd will get reduced, so it will act as an oxidizing agent and it will oxidize this alkene. Always remember, in Wacker process, the addition of oxygen occurs on more substituted carbon. This is really important. Addition of oxygen occurs on more substituted carbon. Am I clear, students? Shall we move ahead? But first of all, please copy this. Now, shall I move ahead? Let's move ahead, students. Okay, now I need to do a one question related to this particular method. I'm having alcohol and this alcohol is secondary alcohol, right? It's treated with a protic acid. What this protic acid will do? Dehydration, right? I will have the formation of alkene. Why alkene? Why not etho? Heat is given, right? At higher temperature. So I will have the formation of alkene. And the alkene which I am going to form will be a ZF alkene, more substituted alkene. So I will remove this OH and I will put one double bond over here. My product A is going to be PH, C, double bond C and C. Am I clear? Why I have put double bond over here? Dehydration reaction, formation of carbocation. Now this alkene will be a Hofmann alkene. Whenever we treat alcohol with a protic acid, we always try to form ZF alkene, the more substituted alkene, the more stable alkene. This alkene is resonance stabilized. Double bond is in conjugation with ring. Now it's treated with PDCl2, CuCl2 in the presence of air, so Wacker process, right? Let me write that WP. WP stands for Wacker process, right? Okay. So basically removal of this pi bond and addition of oxygen on more substituted carbon. Can I say this carbon is going to be the more substituted one? So I'm going to form my ketone as PH, C double bond O, CH2, CH3. This is the product B. Right, students? I hope you understood this Wacker process. Please do copy it, then we'll move ahead. Let's move ahead. Preparation of carbonyl compounds using Grignard reagent. It's one of the most important methods through which we synthesize carbonyl compound. Let's see how does this reaction occur. Reaction of nitrile or cyanide with RMGX. Whenever this cyanide, alkyl cyanide is treated with RMGX, we are going to get ketone as my final product. Okay, there's one case in which we will get aldehyde as my final product if the cyanide is hydrogen cyanide. Let me write that. Student, if I'm having RC triple bond N, let me erase it. RC triple bond N. Okay. If it's treated with RMGX slash H plus slash H2O, the final product, let's write it as R dash MGX. Okay. The final product which I am going to get is R C double bond O R dash plus NH3 gas will get released. Okay. How does this reaction occur? Let us try to understand. C triply bonded N. Can I write this C triple bond N as like this? C double bond N, C positive, N negative. Now, can I say this R dash is having a negative character? It may act as a base as well as a nucleophile. Can I say now this R dash may attack on this carbon? So this R dash is attacking on this carbon. As soon as it attacks over here, this bond will shift over here. So can I say in the first step, I will have the formation of R, C, R dash, double bond, N, negative. Right, students? I hope I am clear till here. And this obviously this MgX will get added here, so it's MgX positive. Now students, I am having RC, R dash, doubly bonded N negative, MgX positive. What I am going to do? I am going to treat it with H plus slash H2O. Right? First, I will have the formation of R. Let me write it over here. C, R dash, doubly bonded NH. Now, RC, R dash, doubly bonded NH. Now I will do the acidified hydrolysis of this one. NH. I will treat it with H plus slash H2O. The product which I will get is R C double bond O R dash plus NH3. So whenever I am having alkyl cyanide, and if you treat it with Grignard reagent, form ketone. Take this R one side of the carbon, this R other side of the carbonylic carbon. In between I will have C double bond O. Right? I hope you understood this one. First, I will have the nucleophilic addition. We'll study this reaction in the chemical properties of carbonyl only. How does this reaction occur? Then we'll have the formation of this imine. This imine on acidified hydrolysis is going to give me RC double bond O R dash. Am I clear? Shall we move ahead? First of all, please copy it. Okay. Student, so can I write if I am having CH3 C triple bond N, and if it's treated with, let us suppose it's treated with CH3 CH2 MgBr first, and then acidified hydrolysis H plus slash H2O. Can you write the product? Yes, easily you can write it, right students? Just take this one CH3, put one carbonyl, this one C double bond O, remove this nitrogen. Now put the other alkyl of Grignard on the right side of this carbonylic carbon. So it's CH2 CH3. My final product is ketone here, right? Okay. If I'm having hydrogen cyanide, HC triple bond N, treated with CH3 MgBr, second step H plus slash H2O, what I will get? Put H, put C, then double bond O, CH3. Just keep as it is, put one doubly bonded oxygen on this carbon, remove this one, add the alkyl part to this carbon. As simple as that. Am I clear? If I am having, let us suppose a cyclic ring, P, this one, C triple bond N. Now if it's treated with CH3 MgBr first, and then acidified hydrolysis, what will be the final product? Can you tell me? You can tell me easily, right? Cyclohexane C double bond O CH3. This will be the final product, students. I hope you understood how do we prepare aldehydes or ketone using Grignard reagent. If I treat Grignard reagent with cyanide or nitrile, I'll generate carbonyl compounds. And this is how the reaction progresses. Please copy it. Preparation of carbonyl compounds using Grignard reagent. Student, we have few more methods through which we can synthesize carbonyl compounds using Grignard reagent only. Okay. If I'm having a substrate like this, RC double bond O G, generally acid derivative. I'm having RC double bond OG, and now if it's treated with Grignard R dash MgX, student, in this particular case, once again we will get ketone as my final product. How does this reaction occur? Let us try to understand. This reaction is referred as SNAE. We'll study this reaction once again in this chapter only. SNAE, addition of nucleophile and then elimination of the leaving group. First the nucleophile is added and then the elimination of leaving group. Nucleophilic substitution, addition, elimination. SNAE. First the nucleophile will attack. Okay. So nucleophile will attack here. As soon as this nucleophile will attack here, can I say this double bond will shift to the oxygen? So can I say I will have RCO negative G and this R dash. Here I will have MgX. Right, students? Now, this is a tetrahedral intermediate, relatively less stable. This oxygen will undergo back delocalization and the Gr group will get departed. So the product which we will get is R C double bond O R dash. Now you may ask, sir, what this group G is? This group G can be OR, it can be O C double bond OR, and it can be X. G can be any of these three species. G belongs to, it can be ester. So basically whenever we treat any acid derivative like ester, anhydride and acyl halide with one equivalent of Grignard reagent, acid derivative, ester, anhydride and acyl halide with one equivalent of Grignard reagent, in that particular case, students, the product is going to be ketone. The reaction will occur via SNAE pathway, nucleophilic substitution, addition, elimination. First, addition of nucleophile, formation of a tetrahedral complex. This tetrahedral complex is or intermediate is relatively a bit unstable. O negative will undergo back delocalization to give me a planar product. Here the hybridization of this carbon is sp2. Here it is sp3. Which carbon is more stable? A planar one. Why? Spacing is more. Bond angle 120 degree. So steric crowding is less here. Am I clear? That's why finally I am going to get ketone as the final product. Acid derivative on treatment with one equivalent. If I am having more than one equivalent, it will undergo further reaction and I will have the formation of alcohols, right? But if I am having only one equivalent of Grignard, in that particular case, my final product is going to be ketone. Please copy it. Using alkanoic anhydride and Grignard reagent. Yes, student, I can have R C double bond O O R anhydride, no? Okay, just a minute. O C double bond O R dash. Now it's treated with R double dash MgX. Right? One equivalent I am only taking. This R double dash will have negative character. Positive one will act as a nucleophile and base. But since here there is no acidic hydrogen, this R dash will act as a nucleophile. It will do the nucleophilic addition on less hindered or more reactive carbonylic carbon. We are going to study about that in this chapter only. Okay. So as soon as it attacks over here, I will have this bond will shift over here. I will have the formation of R C O negative O C double bond O R dash. Now students, what will happen? It will undergo back delocalization. It will act as a leaving group. Why? Because O negative is in resonance with C double bond O. A stable anion may act as a good leaving group, will easily undergo departure, and here I will having this R dash also, R double dash also. This one will depart, so I will have the formation of R C double bond O R double dash. Ketone as my final product. So anhydrides, acyl halides, esters on reaction with one equivalent of Grignard will give me ketone. Once again I am repeating, anhydride, acyl halides and esters on reaction with one equivalent of Grignard will give me ketone as the final product. Please copy it. This one will act as a leaving group. So one of the product is going to be R. This one was R dash. So R dash C double bond O OH. One of the product is ketone, the other one is acid. Please copy it. Students, shall we move ahead? Let's move ahead. Okay. I am having one ester. It's treated with Grignard. Perfect. One equivalent. Here in this Grignard, ET will have a negative charge. This MgBr will have a positive charge, will act as a nucleophile. What it will do? Nucleophilic addition on this carbonylic carbon. As soon as it attacks on this carbonylic carbon, this pi bond will shift over here. So can I say I will have the formation of CH3, CH2, CO negative, OMe, and here I will have ET, ethyl group. Now this O negative, it will undergo back delocalization. As soon as it delocalizes, this OMe will act as a leaving group, will get departed, and I will have the formation of CH3, CH2, C double bond O, ET is nothing but CH2, CH3, ethyl group. Pentrion, right? So ester, acyl halides, anhydrides on reaction with one equivalent of Grignard will generate ketone. Right? Shall we move ahead? Let's move ahead, students. Students, now let's move to the next method through which we can synthesize carbonyl compound. And the method which is there on your screen is Rosenmund reaction. Highly important reaction and one of the most easy reaction. One liner reaction. The substrate here we take is acyl chloride, RC double bond OCl. It's treated with H2 PDBaSO4. We have studied about this particular catalyst, right? Where when we were doing the reduction of alkynes, alkyne was getting reduced to alkene. Student, basically whenever I am having this PDBaSO4, this particular species won't touch a doubly bonded carbon. This one won't reduce, neither it will reduce C double bond C, nor it will reduce C double bond O. So here how the reaction will progress? Simple, you remove this chlorine with hydrogen. Substitution of chlorine with hydrogen. What's the final product? Aldehyde. Aldehyde. So student, whenever you are having acyl halide, acyl chloride, and if it is treated with H2 in the presence of PDBaSO4, remove this halogen, add hydrogen. Substitution or replacement of halogen with hydrogen. This PDBaSO4 won't reduce C double bond O. It won't touch C double bond O. Neither it will touch C double bond C. It won't touch a doubly bonded carbon. I hope I am clear. Right, student? Please copy it. Okay. Let's do one question related to it. CH3, C double bond O, C double bond O, Cl. Propanoyl chloride, right? Now, treated with H2 in the presence of PDBaSO4. What will be the final product? Simple, remove this chlorine, remove chlorine, add hydrogen. The product which will be there is CH3, CH2, C double bond O and H. 1, 2, 3, propanoyl chloride. Any acyl halide on treatment with H2 PDBaSO4, I will get aldehyde, right? Remove chlorine, add hydrogen. Please copy it. Now the next method which we are going to study for the synthesis of carbonyl is difference reaction. Let us try to understand how does this reaction occur. I am having alkyl cyanide once again, RC triple bond N. It is treated with SnCl2 in the presence of HCl. The product which will get here is RC double bond OH, right? So student, keeping alkyl cyanide or nitrile as the substrate, we are having two different methods through which we can generate carbonyl. In one of the method, we will generate aldehydes, whereas in other method, we were generating ketone. Alkyl cyanide treated with Grignard. RC triple bond and treated with Grignard. We were getting ketone. RC triple bond N. SnCl2 in the presence of HCl will get aldehyde. Let us try to understand how does this reaction occur. Student, first here, if I write the mechanism, first we'll do the protonation of this cyanide, nitrogen having lone pair, obviously addition of this H plus on nitrogen, right students? So can I write it like this? RC triple bond N H positive. Nitrogen cannot bear positive charge on it. I will have RC doubly bonded NH positive. Right student? I hope you understood till here. Next, this SnCl2 will undergo oxidation. Here the oxidation state of Sn is +2. Let me write simply Sn +2. I'm having Sn +2. It will undergo oxidation and I will have Sn +4 +2 electron. Now this 2 electron will attack over here. Carbocation plus 2 electron, carbanion. So I will have the formation of Rc negative doubly bonded NH. Next step, H2O. I will have RCH doubly bonded NH. And next step, I will have acidified HCl, dilute HCl I can take acidified water. Hydrolysis of imine always generates carbonyl. I will put one double bond here, will remove NH3 from here. So my final product is going to be RC double bond OH plus NH3. Right student? I hope you understood this particular reaction. Alkyl cyanide on treatment with SnCl2 in the presence of HCl will generate aldehyde, and this particular reaction is referred as Stephen's reaction. Right? Let's move ahead. Please compete. I'm having alkyl cyanide treated with SnCl2 in the presence of HCl. Stephen's reaction. What will be the final product? Aldehyde. Simply remove this one. NH3, nitrogen, NH3, and this one here. Put the cyclohexane on this carbon, put one oxygen, covalency 2. So this is going to be your final product. Alkyl cyanide on treatment with SnCl2 in the presence of HCl will generate aldehyde. One shortcut, RC triple bond N. Remove this nitrogen in the form of NH3 as one of the product. On this carbon, add oxygen. You know how can you add oxygen? The covalency is 2, so oxygen and carbon will form a double bond. Now satisfy the valency of carbon. Right student? I hope you understood it. Let's move ahead. Students, the next method which we are going to study is Oxo process. How does this reaction occur and what we are going to do here? Let us try to understand. Student, this process is also referred as carbonylation of alkene. Carbonylation of alkene. What do we mean by the term carbonylation? Basically, just like Wacker process, it's also oxidation of alkene. Alkene is treated with a reagent and the final product is either aldehyde or ketone. Let's see how does this reaction occur. First, let's write the reaction itself. I'm having one alkene RCH doubly bonded CH2, right? This is the alkene. It's treated with water gas. Can you tell me the formula of water gas? It's nothing but CO plus H2, carbon monoxide plus hydrogen. In the presence of cobalt carbonyl, mainly cobalt tetracarbonyl, this one acts as a catalyst. The product which I am going to get here is R CH H CH2 C double bond OH. Let's see how does this reaction occur. Student, first this CO, that is C negative triply bonded O positive, reacts with hydrogen, and here I will have formation of H C double bond OH. Water gas, basically carbon monoxide, reacts with hydrogen and leads to the formation of formaldehyde. Now this formaldehyde will do addition reaction with this alkene via 4 MCTS, 4 member cyclic transition state. How does this reaction occur? Let's try to understand. I'm having R C H doubly bonded CH2, and this one will get added like this. I'm having C double bond O H, right student, and one H over here. Let's see how does this reaction occur. This hydrogen will get added to this carbon. As soon as this one gets added, this particular pi bond will shift over here, and this one will have a negative character. This one will attack on this one. This negative will attack over here. Simple. 4 MCTS. So what you need to do? Add hydrogen to this carbon and carbonyl C double bond O to the terminal carbon of the alkene. Right? The product now which you are going to get is R C H H CH2, and to this CH2 group, this C double bond OH is getting added. Right? This is my final product. So student, in oxo process generally we are going to get aldehyde. In Wacker process generally we get ketone, whereas in the oxo process mainly we get aldehyde. I hope this particular concept is also crystal clear. Please copy it. Next one, Reimer-Tiemann reaction. You have studied this reaction, right? Phenol. I'm having phenol treated with chloroform CHCl3 in the presence of NaOH, heated. The product which we were getting was orthohydroxybenzoaldehyde, OH, C double bond OH. Apart from this, one more product was there, that is OH, C double bond OH, para-hydroxybenzoaldehyde. Para-hydroxybenzoaldehyde, and one of them is orthohydroxybenzoaldehyde. Which one is the major one? This one. Why this is major? Because of intramolecular hydrogen bonding, IMHB. Right students? Please do copy it. The next method, and this particular method we have already studied, it's simply a revision. Once again I am having acyl halide, and now it is treated with an organometallic R2CD. Here once again this chlorine will get replaced by this alkyl group. Simple. Remove this chlorine and you need to simply replace this chlorine with R dash negative. Right? This reaction is also, you can say, occurring via SNAE pathway, just like Grignard. R2CD, it's also an organometallic, will do the nucleophilic addition, and then I will have elimination of the leaving group and formation of ketone. Right students? Shall we move ahead? Let's move ahead. The next reaction which we are going to study is Fiddle-Craft acylation reaction. In this reaction, I will take benzene as a substrate, and one of the substrate will be acyl halide. Both of them are treated with a Lewis acid AlCl3, and then I will have the formation of ketone. Let's see how does this reaction occur. Student, I'm having benzene C6H6, and it's treated with C6H5 5 C double bond OCl. Let's write that also. Benzoyl chloride, right? C double bond OCl. Now it's treated with AlCl3. First, this benzoyl chloride will react with AlCl3. This is Lewis acid. I will have the formation of pH C double bond O positive plus AlCl4 negative. I should not bother about this AlCl4. Now, this pH C double bond O positive will act as a electrophile, and what it will do? Electrophilic aromatic substitution reaction with this benzene. Simply, we have studied in benzene on each carbon we are having one hydrogen. What you need to do in this electrophilic aromatic substitution, simply remove one hydrogen and replace it by your real attacking electrophile, the main electrophile. And here the electrophile is pH C double bond O positive. So what you will write as the product? pH, and on one carbon you will simply substitute this one, and it's nothing but C double bond O pH, right? I hope you understood this one, benzophenone as the final product. Let's do one question more. Student, I'm having benzene as my substrate, and now it's treated with CH3, CH2, CH2, C double bond O, Cl. Okay, in the presence of a Lewis acid AlCl3. First, this acyl halide will react with the Lewis acid AlCl3, and I will have the formation of carbocation, that is CH3, CH2, CH2, C double bond O positive. Now this carbocation will act as a real attacking electrophile. Will it undergo rearrangement? The answer is no. Now you will say, sir, you have only told whenever a carbocation is formed, it will undergo rearrangement, and now you are saying it won't undergo rearrangement. Student, because here the carbocation which we are forming is the most stable carbocation. Why? Because this carbocation is stabilized by back bonding of oxygen, right? Okay, so it won't undergo rearrangement. Simply you need to substitute it on benzene. So the product will be pH C double bond O CH2 CH2 and CH3, right? This is the final product. I hope you understood this Fiddle-Craft alkylation, Fiddle-Craft acylation reaction, not alkylation reaction, right? It's acylation reaction, and through this Fiddle-Craft acylation reaction we generate carbonyl compounds, right? Mainly ketone. Next method which we are going to do is Decalboxylation method. Although we'll study about this particular reaction in detail in the next chapter with detailed mechanism, here we are simply going to brief this reaction. You should simply know about this reaction. What do we mean by the term beta keto acid? Let's simply try to understand it. Okay, we'll discuss this reaction in a complete detailed way with a proper mechanism in the next chapter when we'll be talking about the different decarboxylation methods. Okay, student, I'm having ester. This ester is treated with acidified water. Ester on acidic hydrolysis gives acid plus alcohol. Whenever acid and alcohol react, they form ester. Ester on acidified hydrolysis will generate acid and alcohol. Now, the acid which I am getting is a beta keto acid. Why? Yes. Can I say this is my carboxylic group? Now, can I say this carbon as my alpha carbon? Right? Carbon containing this carboxylic group, the functional group is the alpha carbon. So can I say the next carbon is going to be the beta carbon? And on this beta carbon I am having a carbonylic, that is I am having C double bond O, right? So can I say this species as a beta keto acid? Why? Because if I write the structure CH3 C double bond O CH2 C double bond O OH. With respect to this carbonylic carbon, this C double bond O is at beta position, or I can say with respect to this acid, it's at beta position, so beta keto acid. Now whenever this beta keto acid it is heated strongly, it readily undergo decarboxylation. What do we mean by decarboxylation? Removal of CO2. So CO2 will get removed from this acid, this hydrogen will get added to this carbon, and I will have the formation of ketone along with CO2. Okay, student, this is how this reaction occur, but right now I am not going to discuss this mechanism. We'll discuss this mechanism in the next chapter, acid derivative. Okay, please wait till then. Student, let's do one question in order to understand this decarboxylation technique. First, let us try to understand what do we mean by beta keto acid. How do we recognize whether an acid is a beta keto acid or not? Is this a beta keto acid? Is this acid and a beta keto acid? Tell me. And what will happen if I heat it strongly? Student, if we look at this particular acid, can I say this carbon is the alpha carbon, and the neighboring carbon of this alpha carbon means this one and this one, both of them are the beta carbon, and this beta carbon is having a carbonylic group, or it's nothing but a carbonylic carbon. So can I say this acid as beta keto acid? With respect to this acidic group, carbonylic carbon is at beta position. And whenever a beta keto acid is heated strongly, you simply remove CO2 from this carboxylic acid, add this hydrogen to alpha carbon. So the product which we'll have is this one, right? Cyclohexanone. Student, I hope you understood this method also. Students, so this was all about GMP of carbonyl compounds. Friends, now it's time to discuss the chemical properties of carbonyl compound. And the most important reaction which we are going to discuss now is nucleophilic addition reaction. We have studied one more type of addition reaction, and that was in case of hydrocarbon. There we had studied electrophilic addition reaction. Now we are going to discuss about nucleophilic addition reaction. So this particular reaction will be initiated by a nucleophile. Let's try to understand this reaction. In short form, we say this nucleophilic addition reaction as AN reaction. Nucleophilic addition reaction. Okay. Student, I am having a carbonyl compound RC double bond O. I can have H. If it's H, aldehyde, I can have R also, R dash also. Then it's ketone. Right? Now, any one of them is treated with a nucleophile Nu minus. Nucleophile is the electron rich species. We have studied all these things, right? Now what this nucleophile will do? The tendency of nucleophile is to attack on electron deficient species, right? Now if I look at this C double bond O, can I say it's always polar? Because of electromeric effect, I can write it like this, C plus O negative. Now can I say this carbon will act as the electrophilic center? So nucleophile will do the addition reaction on this carbonylic carbon, right? So now this nucleophile will attack on this carbon. As soon as it attacks, this particular pi bond will shift on oxygen, and I will have the formation of product like this, O negative, H and Nu. Now student, if we look at this particular reaction, let's first of all focus on substrate. What is the hybridization of this carbon? sp2, geometry, planar. What is the hybridization of the product? It's nothing but sp3. So geometry, tetrahedral. What do you say? Which one is more stable? A planar or a tetrahedral? Planar, right? Because there the spacing is more, steric crowding is less. Right, students? Okay, so can I say this particular reaction, in this reaction, a more stable reactant is relatively giving a less stable product. So the reaction will not be irreversible. It won't be a unidirectional reaction. It can be a reversible reaction. Anytime this O negative can delocalize and can give me NU, right? So this particular reaction, this AN reaction, is a highly reversible reaction. I hope you understood. First, on the carbonylic carbon, the nucleophile will attack. As soon as it attacks, it will get attached to this carbon. I will have a tetrahedral intermediate, or you can say product, right? Now here, it will simply take solvent from water, and I can have formation of RCOHHNU, right? Simple. Now, students, now you may say, okay sir, so this is the nucleophile and it's attacking on the carbonylic carbon and I am getting a tetrahedral intermediate, or we can say a tetrahedral product, where the nucleophile is getting added to the carbonylic carbon. Can you tell me the factor which affects this AN reaction? What are the different factors which is having a significant impact on this AN reaction? Let's try to understand this. Factors affecting AN reaction. AN reaction. That is nucleophilic addition reaction. Student, the first factor which affects the AN reaction is nucleophilicity of the nucleophile. If the nucleophile is strong, right, then it will easily attack on this carbonylic carbon and reaction will be shifted in the forward direction. So if I am having a strong nucleophile, reaction will always shift in forward direction. Then this bond will be very strong. The tendency of this bond to cleave will be very less, right? So if the nucleophile is strong, reaction will be favored in the forward direction. I will have more amount of this product getting formed, right? So first factor which affects is nucleophilicity of nucleophile. Nucleophilicity of NU minus. What does this mean? A strong nucleophile. Strong nucleophile will favor AN reaction. The second one, where this nucleophile is attacking. Is it attacking on carbonylic carbon? And if this carbonylic carbon is more reactive, can I say the attack of nucleophile will be faster? Right? So can I say the second factor which affects nucleophilic addition reaction is reactivity of carbonylic carbon, C double bond O. Now, what are the factors which will contribute to the reactivity of this carbonylic carbon? Let us try to understand. I'm having this carbonylic carbon, right? And on this carbonylic carbon, a nucleophile is attacking. If steric crowding is less, can I say in that particular case the nucleophile may approach on this carbon very easily? If the bulkiness is less, if there is small group like hydrogen, then the nucleophile can easily approach here. Reactivity will be more, right? So can I say lesser the steric crowding, faster will be the rate of AN reaction? Right? So can I say lesser the steric crowding on this carbonylic carbon, faster will be the rate of AN reaction. Now you only tell me in this case 1 and case 2, where the steric crowding on carbonylic carbon is less. In case of aldehydes, right? Because in case of aldehydes, on one side I am having a very small group, hydrogen, right? So steric crowding is very less, whereas in ketone the steric crowding is relatively more. So it will be very tough for nucleophile to approach on this carbonylic carbon. That's why aldehydes are always more reactive for AN as compared to ketones, because in ketones we are having steric crowding, we are having bulky alkyl groups on either side of carbonylic carbon, right? So reactivity of carbonyl, and the factors which will impact the reactivity of carbonyl is lesser steric crowding, crowding. One more factor Okay, there is one factor which is contributing to this AN reaction is steric crowding. Lesser the steric crowding, faster will be the attack of nucleophile, better will be the rate of AN reaction. One more factor. And what is that factor? Student, we have studied this nucleophile is attacking on C positive, right? Because the C double bond is highly polar, it splits as C plus O negative. So can I say more is the positive charge on this carbon, faster will or better will be the affinity of nucleophile to attack on this carbon, right? More the electron deficiency on carbonylic carbon, faster will be the approach of nucleophile on this carbonylic carbon, better will be the rate of AN reaction. So can I say even the electron deficiency on carbonylic carbon, more the electron deficiency on C double bond O, faster will be the attack. Because the electron rich species will always be in need of highly electron deficient species. More is the del positive on the carbonylic carbon and more is the del negative on the nucleophile, stronger will be the CNU bond, right student? So more the electron deficiency, faster will be the rate of AN reaction. Now, so can I say if an electron withdrawing group is connected to this carbonylic carbon, the rate of AN reaction will be more. If an electron donating group is attached to this carbonylic carbon, the rate of AN reaction is going to be less, right? Electron withdrawing group will increase AN reaction, whereas electron donating group will decrease the rate of this AN reaction. I hope you understood this AN reaction, right? Let's move ahead, student. Okay, the correct order of rate of reaction towards nucleophilic addition reaction. Yeah, this is the question which I wanted. I am giving you 1 minute. Try it on your own and then we'll discuss it after 1 minute, student. Okay, let's start. Have you attempted this particular question? Shall we start now? Let's start. You only tell me, between aldehydes and ketone, which one is more reactive for AN? Aldehyde, right? Now, between acetaldehydes and benzaldehyde, which one will be more reactive? What do you say? Acetaldehydes or benzaldehyde? Student, acetaldehyde is more reactive as compared to benzaldehyde. Why? Because in case of benzaldehydes, I am having this pH group which acts as a very weak plus M, right? So the reactivity of the carbonylic carbon will be less. One more factor, this phenyl group is really bulky group, right? More the steric crowding, lesser is the reactivity. More is the steric crowding, lesser the reactivity. Now you can solve this question in less than 30 seconds. If we look at these three options, we have this one, and this one. All of them are benzaldehyde derivatives, right? Aldehydes more reactive than ketone. If we look at this one, then this one, all these 5, 1, 2, 3, 4, 5, they are aldehydes, right? 4 and 7, they are ketones. So obviously these two are going to be least reactive. Am I clear? These two will be less reactive as compared to 1, 2, 3, 5 and 6. Now, between this 1, 2, 3, 5 and 6, which one will be more reactive? Student, aldehydes, acetaldehydes, acetaldehydes. CH3, CH3. Hydrogen, here I am having chlorine. And this chlorine will act as a strong minus I group. What this minus I will do? It will increase the reactivity of this carbonylic carbon, right? It will increase delta positive on this carbon. So nucleophile can easily attack here. More is the electron withdrawing group, faster the rate of AN reaction. So can I say this 6 is going to be more reactive than 5? 6 max, then we will have 5, right? Now, and these two will be more reactive than benzaldehyde's derivative. Now let's focus on benzaldehyde derivative. NO2 minus I minus M will increase the reactivity. Reference plus M will decrease the reactivity. So can I say here the relative order will be 1, 2, 3 among these three benzaldehydes? Minus I group and minus M group will increase the reactivity of carbonylic carbon. So after 6, 5, then I will have 1, then I will have 2, then I will have 3. And now between 4 and 7, methyl group, C double bond O, C double bond O. ET, pH, more bulky, more is the steric crowding, lesser the attack of nucleophile, right? Because nucleophile will have a lot of difficulty to attack on this carbonylic carbon, right? So which one will be more reactive? 4. Why 7 is less reactive? Because of more steric crowding, more bulky groups attached to the carbonylic carbon. So 3, then I will have 4, and then I will have 7. I hope you understood this one, students. Am I clear? Is this concept of rate of nucleophilic addition reaction clear? Is the question clear? Let's move ahead. This question is really important. Lot of times questions will be asked directly or indirectly on this particular concept, rate of AN reaction. So this is really important. Let's move ahead. Students, now it's time to discuss the application of AN reaction. And the first reaction which we are going to do is addition of alcohol on carbonylic carbon. Let us try to understand this reaction. Highly important reaction for all the competitive exam, whether it is NEET, JEE mains and advanced. Simply you need to focus on this particular reaction. Shall we start? Let's start. I'm having a carbonylic carbon. Can I take aldehyde? Let's take aldehyde itself. Aldehyde in general is more reactive. Okay. Now it's treated with 2 moles of alcohol, ROH, in the presence of a catalyst HCl. The product which we get is RCOR H. This is the final product along with H2O. That's a different story. And this is referred as a very important compound, and this compound is referred as acetal. Acetal. But before the formation of acetal, there is formation of a very important compound, and that is hemiacetal. How does this reaction occur? Let us try to understand the mechanism of this reaction. Aldehydes or ketones treated with 2 moles of alcohol gives to the formation of acetal. If it is aldehyde, acetal. If it is ketone, we'll have ketal. Okay. Now, let's try to understand the mechanism. I'm having aldehyde. It's treated, first of all, it is treated with HCl. Why? Because we know this ROH is a moderate to poor type of nucleophile. It's not a strong electrophile. And for AN reaction, the nucleophilicity should be very high. If the nucleophilicity is not that high, then we increase the reactivity of carbonylic carbon. And it can be done by using the catalyst acid. What this acid will do? It's a source of H+. Where it will attack? It will attack on this oxygen, right, student? Okay. So can I say I will have the formation of RC double bond OH positive and H. Now oxygen cannot bear positive charge on it. So can I say this particular pi bond will shift here, and I will have RC positive OH and H. Now here, now I'm having a complete positive charge. Here the role of nucleophile will come into picture. This nucleophile will do the nucleophilic attack on this electrophilic site. I will have the formation of a highly important compound, and that is RCOH. Let me write H over here, and this nucleophile is getting added, so OH, R, and this O will have a positive charge. It has donated a lone pair. It will readily undergo deprotonation, and finally I will have the formation of RCOH, OR and H, and this particular compound is referred as hemiacetal. So aldehydes or ketones. Let's first of all talk about aldehyde only. Aldehyde on treatment with 1 mole of alcohol will generate hemiacetal. How will I identify whether the given compound, or how can we identify the given compound is hemiacetal or acetal? Student, I am giving you a simple trick. Focus on the carbon containing oxygen. If this carbon is containing one OH, one OR and one hydrogen, it is hemiacetal. Focus on the carbon containing oxygen. Now check which groups are connected. If it is having one alcoholic group, one ether group and one hydrogen, it is hemiacetal. Am I clear? Now this hemiacetal is further treated with HCl and 1 more mole of alcohol is there. What this HCl will do? Will protonate alcohol. Then it will get departed in the form of H2O, right? I will have the formation of RCOH, H positive, OR and H. Now the nucleophile will easily approach here. It will attack here. This one will depart, and I will have the formation of RCOR. 1 more alcohol is getting added, so 1 OR. Right? Now this carbon is containing 2 ether group. Carbon containing 2 ether group and 1 hydrogen is referred as acetal. Carbon containing 1 hydroxyl group, 1 OR group and 1 hydrogen, hemiacetal. In the same way, we can generate hemiketal and ketal. Instead of taking aldehyde, we can take ketone here. Now the carbon containing oxygen, OR and alkyl group, no hydrogen, then it is hemiketal. Here, instead of hydrogen, if this hydrogen is replaced by a alkyl group, I will have the formation of ketal. So from ketone, we can generate hemiketal and ketal. From aldehydes, we can generate hemiacetal and acetal. Am I clear, students? From aldehydes, we can generate hemiacetal and acetal. From ketone, we can generate hemiketal and ketal. Let's move ahead. Which of the following compound is hemiacetal? This is very important. Lot of time we need to identify whether my given compound is hemiacetal or not. Okay, how can we identify easily? Simply focus on the carbon containing oxygen, which is attached to oxygen. So here this carbon. Now it's having OH, OR, perfect. 1 OH and 1 OR. Is there any hydrogen on this carbon? No. So can I say this compound as? Both alkyl groups are there. Carbon containing 2 alkyl group, 1 OH, 1 OR is hemiketal. Hemiketal. Right? Next one. Let's focus on this carbon. 1 OR group, perfect. 1 OH group, perfect. 1 hydrogen is also there. Carbon containing H, OH and this entire alkyl group, hemiacetal. Hemiacetal. Let's move to the next one. Carbon containing OH, OR and H, hemiacetal. Okay, this one. Focus on this particular carbon. Carbon is containing OH, hydrogen also, right? And then it is connected to OR group also, hemiacetal. Right, student? C containing OH, H, and this is connected to oxygen. Carbon containing OH, OR and hydrogen is nothing but hemiacetal. So this one is also hemiacetal. I hope this particular question is crystal clear to all of you. Is this clear? Okay. Student, now let me tell you one very important property of this hemiacetal. If I look at this particular compound COH, O, Me, H and alkyl group. This is hemiacetal, right? Now if I focus here, I'm having CO bonded to H, and at the same time this carbon is having one more oxygen also. Can I say I can have intramolecular H bonding here? Right? 1, 2, 3, 4, 4-member cyclic ring formation in hemiacetal. And whenever I'm having a 4-member cyclic ring formation, that compound will be highly unstable. That compound will be highly unstable. So this intermediate hemiacetal which is formed is relatively unstable. Why? Because of 4-member cyclization, 4-member chelation, because of intramolecular hydrogen bond. Here this intramolecular H bonding is decreasing the stability of this hemiacetal. Now between hemiacetal and acetal, which one is more stable? Acetal. Why? Because in case of acetal, we don't have any 4-member cyclization. There is no hydrogen bonding, right? So hemiacetal is relatively less stable as compared to acetal. Let's move ahead. Students, now it's time to discuss a very important question which is there on the screen. Let's focus on this particular question. In this question, I'm having aldehydic part and keto part. This one is aldehydes, ketone, and it's treated with one equivalent of ethylene glycol. Now the first question is whether this ethylene glycol will attack on the aldehydic part or keto part. Which one is more reactive? Can you tell me? Aldehydes. So where it will attack? Here. Now, what will be the final product? How can you write directly without writing the mechanism? I'm giving you a shortcut. Student, whenever you are having 2 moles of alcohol and it's treated with aldehyde, this aldehyde treated with 2 moles of alcohol, what you need to do, remove hydrogen from alcohol, simply take this OR group, the nucleophilic part, remove this oxygen from carbonyl and add 2 OR bond. Add 2 OR bonds. So what is the product? R, C, OR, OR, H. So basically you are removing 2 hydrogen from here, 1 oxygen from here, you are removing water, right? Elimination of water and formation of acetal. Now, if we focus on this particular substrate, I'm having ethylene glycol, a dihydric alcohol. Both of them will attack here, and on this carbonylic carbon, what I am going to do? I am going to remove first this hydrogen, and this particular oxygen, and now I will connect both the oxygen to this carbon. So can I say my product will be like this, right? And now this carbon will get connected to 2 oxygen, and this oxygen is like this, right? So I'm having a formation of cyclic acetal, okay, or ketal you can say. Now it's treated with CH3 MgBr. Student, now let me tell you one thing, MgBr. This acetal, ketal is not reactive with a base. Why? Because it's having a lone pair. It is this acetal is having a basic character. It acts as a Lewis base. So a base is not going to react with a base or electron rich species. This acetal, this ketal is reactive with acid. And whenever the acetal or ketal is treated with acid, we simply get carbonyl plus alcohol. This reaction is highly reversible. Aldehydes or carbonyl plus alcohol gives acetal, right? Now acetal on treatment with acid will give me carbonyl plus alcohol. Reversible reaction. Okay. So this CH3 MgBr won't attack on this acetal part. Then where it will attack? On this carbonylic carbon, nucleophilic addition reaction. This CH3 minus will attack over here. This one will shift, and I will have the formation of B as the product B will be OH, CH3, and here I'm having my acetal or ketal, right? This is the product B. Now it is treated with acidified water, H plus slash H2O. Student, whenever this acetal or ketal is kept in acidic medium, it gives us back aldehyde and alcohol. So what will be my final product? Once again, I will get back my aldehyde. Now this one, OH, CH3, C double bond OH plus ethylene glycol. I hope this question is clear to you all. Please copy it. Let's move ahead, student, now. Okay, great. So now I'm having one more acetal type of species. See, carbon containing 2 OR. It can be acetal, it can be ketal. If it's having hydrogen, acetal, right? Okay. Now, whenever this acetal is treated with H plus, simply you need to do one thing. Break this bond. Okay. Put one OH over here, one OH over here, and on this oxygen put H and H. So what will be the product you will get? OH. Here I'm having alcohol, OH, OH, and now on this carbon I'm having 2 OH, right? H and H. Geminal hydroxyl system, highly unstable, readily loses 1 mole of water and will give me HC double bond OH, right? So one of the product is going to be formaldehyde and the next one is this one. Simply whenever you see any cyclic acetal or ketal, cleaves CO bond, add H to both the oxygen, and now add OH to the carbon part also connected to this ring. Am I clear? Let's move ahead. One more important method. Student, this is the method through which from carbonyl compound we can synthesize alkane. And this particular reaction is referred as Mojingo reaction. How does this reaction occur? Same way, instead of alcohol, I am having SH group. So instead of O, I am having S. So now this S will get connected to this carbon. I need to remove this H. I need to remove this H. I need to remove this one. And then I will have the formation of a cyclic product. CH3, C, CH3. And this one's S and S connected to CH2, CH2. Now it is treated with Raney nickel. Raney nickel we have studied in hydrocarbon itself. What it will do? Reduction. Simply, I will have the formation of NIS, and here I will break this one once again, and I will add 2 hydrogen over here. So I will have my final product as CHH, CH3 plus, and here this alkane is formed, and along with that this NIS is also formed. But for me this NIS and the byproduct is not that important. Here the important part is carbonyl on treatment with the substrate in the presence of Raney nickel gives us alkane. This is a reduction reaction of carbonyl. This is how we can synthesize alkane from carbonyl compound, and the name of this reaction is Mojingo reaction. Okay, shall we move ahead? Let's move ahead. Students, now let's move to the next application of nucleophilic addition reaction, and now we are going to do addition of HCN, or basically the addition of CN minus to a carbonylic carbon. This CN minus gets added to aldehyde as well as ketone, and the product formed is cyanohydrate. Let's see how does this reaction occur. Student, here I'm having an aldehyde. Now this aldehyde is treated with a nucleophile cyanide ion in the presence of an acid HCl. Basically we take catalytic amount of this HCl, mainly acts as a catalyst. What it will do? It will promote the rate of, or it will increase the rate of nucleophilic addition reaction. what it will do, it will mainly act as a source of H plus. This H plus will protonate this oxygen. So now I will have a protonated carbonyl like this H. Now the reactivity of this carbon has increased because the electron cloud will be shifted towards positively charged oxygen. As soon as this electron cloud shifts towards oxygen, the nucleophile cyanide ion will attack here, and I will have the formation of my product as R, C, OH, CN, and H. And this is referred as cyanohydrine. Cyanohydrine. So this cyanide ion adds to carbonylic carbon, and the product formed is cyanohydrine, a tetrahedral species, right? sp3 hybridized. This reaction is also highly reversible. So shall we move ahead? First of all, please copy it. Students, now let's move ahead. Now this addition of water to carbonyl. This reaction is really important, and lot of time questions are asked on this particular concept. Let's try to understand this particular reaction. Student, let's take a carbonyl aldehyde itself. Okay. Now, this is treated with a nucleophile water. Here water is acting as a nucleophile. Obviously this nucleophile is a very poor nucleophile. So in order to increase the rate of reaction, we need a catalyst. We'll take slight amount of or little amount of HCl. Okay, we are going to take small amount of this acid HCl. What this acid HCl will do? First it will release H plus, and this H plus, what it will do? It will protonate this carbonylic carbon, right? So I will have R, C, double bond O, H, positive H. I can write it like this: R, C, OH, H, positive. And here on this positively charged carbon, water will attack here, right? It's a moderate to poor type of nucleophile. Now it will do the nucleophilic addition reaction here, and I will have the formation of R, C, OH, OH, H, H. Oxygen having positive charge will easily undergo deprotonation, and I will have the formation of R, C, OH, OH, H. Student, it is referred as hydrate. It's nothing but geminal hydroxyl system referred as hydrate. So carbonyl compound adds to water and forms hydrate. Now, if I look at this particular reaction, student, this reaction is highly reversible reaction, because we have studied a geminal hydroxyl system. What do we mean by geminal hydroxyl? Carbon containing two OH group is relatively unstable, right? Because of four-member intramolecular hydrogen bonding. So this reaction is highly reversible reaction. Students, first of all, let us write this reaction once again. I'm having a carbonyl compound, R, C, double bond O, H. It's treated with water, and I am getting my product as RCOH, OH, H. And it's nothing but hydrate, geminal hydroxyl system. Students, if this process is reversible, obviously we can define equilibrium constant here, right? And can I write K equilibrium is nothing but concentration of hydrate RCOH, OH, H upon concentration of substrate, that is RC double bond OH, into concentration of water. Obviously this one is taken in excess, so basically it's a ratio of hydrate upon aldehyde. Now most of the cases what you will find, this hydrate is highly unstable, so most of the time reaction will shift in the backward direction, right? Maximum time I will have aldehyde as the major one, and All the hydrate will be there, but it will be present in very less amount. But can we increase the concentration of hydrate? Yes. So now we are going to discuss the factors which increases the stability of hydrate, or we can say which increases the concentration of hydrate at equilibrium. Okay. Student, no doubt this water is a poor nucleophile, right? This is a poor nucleophile. So it will have a very less tendency to do addition reaction with this carbonylic carbon. But anyhow, if I increase the reactivity of this carbonylic carbon, can I say in that particular case, the reaction may shift in the forward direction? Right? So if I have to increase hydrate concentration at equilibrium, I have to make this carbonyl more reactive. Right? Now, what are the different factors which may increase the reactivity of this carbonylic carbon? First, steric crowding. Lesser the steric crowding, more will be the hydrate formation. Lesser the steric crowding, more will be the hydrate, or more will be the concentration of hydrate at equilibrium, or more will be the stability of hydrate at equilibrium. Am I clear? So stability of hydrate at equilibrium depends on reactivity of this carbonylic carbon. Lesser the steric crowding, more is the stability of hydrate. Am I clear? One more factor. More is the reactivity, means more is the del positive charge on this carbon, on this electrophilic carbon or the carbonylic carbon. More is the electron deficiency on this carbonylic carbon, better is the stability of hydrate, or more is the concentration of hydrate, or I can say more will be the K equilibrium constant value. Am I clear? So stability of hydrate, concentration of hydrate, or K equilibrium value will depend on first lesser steric crowding on the carbonylic carbon and more electron withdrawing groups connected to this carbonylic carbon. More is the EWG connected to this carbonylic carbon, higher will be the electron deficiency here, better will be the stability of hydrate. Am I clear? Please copy it. Now, compare the rate of hydrate formation of the following. Student, simply rate of hydrate formation, stability of hydrate, K equilibrium simply depends on one factor. Reactivity of carbonyl. Lesser the steric crowding and more is the electron withdrawing group connected to it. Higher will be the hydrate formation, or higher will be the rate of hydrate formation, or we can say higher will be the concentration of hydrate at equilibrium. Okay. Formaldehyde. Okay, then we have HC double bond OCl, then we have HC double bond OCH3, then we have ketone, then we have benzodiazepine, and then we have once again benzophenone. We have studied this, right? In general, aldehydes are more reactive than ketone for nucleophilic addition reaction. The same case here also. So all these aldehydes will be more reactive as compared to ketones. Now in case of aldehydes also, if I increase the reactivity of the carbonylic carbon by attaching electron withdrawing group, the hydrate formation ability will increase. Am I clear? Okay. So among these three, what do you say? Which one will be more reactive with water? Or which one will give more stable hydrate? This one, formyl chloride. So second maximum, then I will have, let me use white one. Then we will have formaldehyde. Between formaldehyde and formyl chloride, formyl chloride is more reactive because of the presence of electron withdrawing group. Then we will have formaldehydes. Then we have acetaldehydes, third one. Then we will have between 4, 5 and 6. Fifth one is once again aldehydic group. So then we will have fifth. Now between this fourth and sixth, steric crowding is less here in case of propanol. So then we'll have fourth one, and in sixth one, steric crowding is maximum, right? So here the hydrate form will be highly unstable. Least sixth one. I hope you understood this one also. Shall we move ahead, students? Please copy it first of all. Addition elimination reaction. Students, till yet mainly we were talking about addition reaction. Now it's time to discuss SN-AE reactions on carbonyl. Let's see how does this reaction occur. We have already studied it. It's simply a revision. Student, whenever I am having an acid derivative, and now if this acid derivative is treated with a nucleophile Nu minus, what this nucleophile will do? First it will do nucleophilic addition reaction on this acid derivative, right? And we have studied that addition of nucleophile to a carbonylic carbon is highly reversible process. Okay, so this one will attack over here. As soon as it attacks over here, this particular pi bond will shift to the oxygen part, right? So I will have R, C, O negative, G and Nu. Now, can I say, if I have to compare the stability between the reactant and the product, which one is more stable? Can you tell me which one is more stable? Whether the reactant is more stable or the product? Obviously the reactant, right? So still here the reaction is shifted in the backward direction. If the nucleophile is weak, easily this O negative will delocalize and Nu will get departed. But if this nucleophile is stronger than this G, if CNU bond is stronger than CG bond, which one will cleave? The one which is weaker, right? So if CG bond is weaker, as soon as this O negative will delocalize, this will get departed. So can I say I will have the formation of R double bond C and U. So what's happening here? A nucleophile is replacing this group, leaving group, right? Mainly we see such types of reaction in case of acid derivative. If this G is OR, O C double bond OR, X, in all such case, if it's treated with, if any of these acid derivatives are treated with a nucleophile, first it will do nucleophilic addition reaction. I will have a tetrahedral intermediate. Here this tetrahedral intermediate is highly unstable, so this O negative will undergo back delocalization. As soon as it delocalizes, this CG bond will cleave, G will act as a leaving group, it will get departed in the form of G minus, and I will have once again my planar species R C double bond O Nu getting formed. So here the nucleophile is simply replacing this G. And what is G? It can be S2, it can be OR, it can be OC double bond OR, it can be X. So basically this SN-AE reaction occurs in case of ester, acyl halides and anhydrides. SN-AE reaction. Right? We have studied this reaction a lot of times from alcohol onwards, right? Let's move ahead. We have one more reaction which is based on the application of this addition elimination reaction. Let us try to understand that reaction also. Addition of NH2Z derivative to carbonyl compounds. Carbonyl compounds. Let's try to understand how does this reaction occur. I'm having a carbonyl compound RC double bond OH. Now it's treated with ammonia derivative NH2Z. Okay, this Z can be anything, can be alkyl group, can be hydrogen, can be OH, can be NH2, anything. Okay, you don't need to bother about this Z. I'm having a carbonyl compound. This carbonyl compound is treated with NH2Z. Here we take small amount of HCl. The product which we form is R C double bond N Z H. If we look at this particular reaction, what I have done, I have removed this oxygen. I have removed both the hydrogen connected to nitrogen. Basically, I have removed water molecule from here and I have formed RC double bond NZH. Okay, let us try to understand the mechanism of this reaction. Student, once again, this HCl, what it will do? It will mainly protonate this carbonylic carbon, or we can say it will protonate oxygen. Now this, on this carbon, NH2Z will attack. It will act as a nucleophile. I will have nucleophilic addition reaction. I will have the formation of RCOH, right, H, and then I will have NHHZ, right? Okay. Now, student, obviously we have this nitrogen cannot bear positive charge, so it will readily undergo deprotonation, and I will have RCHOH, and here I will have NZH lone pair, right? Now, carbon containing OH and NH. In both these species, I am having lone pair. So what will happen here? Here, students, this lone pair will delocalize, and as soon as this one delocalizes, OH will act as a leaving group and it has to depart. So I will have the formation of R C H doubly bond N H Z positive, right? Nitrogen cannot bear positive charge on it, so I will have finally the formation of R C H double bond N Z, right? Okay, this particular species is mainly referred as imine derivative. I will explain. Okay, let's see. I can have R aniline compound. Let me take CH3 C double bond OH, and now it's treated with ammonia NH3 in the presence of HCl. What will happen? What will be the product here? What you need to do? Simply break this one as NH2Z. NH2Z. So what is Z here? Hydrogen only. This is Z. Now what you need to do? Shortcut. Remove this two hydrogen and this oxygen, and now add simply C double bond N Z. So the product which will form is CH3 C double bond N H, right, plus water, and this is nothing but imine, right, student? I can replace this Z by even alkyl group also. Let's take one example. I'm having CH3 C double bond O CH3. Now I am taking ketone and it's treated with primary amines CH3 NH2 in the presence of HCl. Can you tell me the product? Simply. Now this one will act as a group Z. 2 hydrogen, 1 oxygen you need to remove. You need to add CH3 C double bond N CH3. CH3 C double bond N Z. This is nothing but Z. Okay, I can take CH3 C double bond H, and now I am going to treat it with NH2OH. Can you tell me what is Z here? This OH group. What will be the product here? CH3 C double bond N OH. It's nothing but oxime. Now, student, if I talk about the pH of this particular reaction, the pH taken is generally 4.5 to 5. The reason is, if we'll take highly acidic condition, in that particular case, what will happen? this H plus will protonate the nucleophile itself, right? So the nucleophilicity of the nucleophile will decrease and the reaction will not occur. So the optimum pH required for this particular reaction is 4.5 to 5. Okay, let's do 1 to 2 more questions related to this concept. Student, I can have CFPH like this. Now I'm having cyclic keto and now it's treated with NH2, NH2. Can you tell me the Z? What is Z here? NH2, 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 and now I can take this one as Z. Taken in the presence of HCl, small amount of HCl. What will be the product? C double bond NZ. Double bond N. You need to remove this H2, you need to remove this oxygen, and now simply replace it by NH2. Am I clear? Okay, let's move ahead, student. Yeah, so these are some of the important reactions of this carbonyl with ammonia derivative. Although we have done this, but now it's time to discuss even the name of this product also. This name is also really important. Let's discuss it one by one. Carbonyl compound treated with NH2OH. Z is OH here. C double bond NZ. The product formed is referred as oxygens. Next one. Carbonyl compound treated with phenylhydrazine. pH NH NH2. Can you tell me what is Z here? Student, if I talk about Z, this is my Z group. What will be the product? You need to remove this oxygen, add doubly bond NZ. C double bond N, and this entire group is your Z group. The product formed is phenylhydrazone. So I'm having carbonyl compound. I'm treating this carbonyl compound with phenylhydrazine. The product formed is phenylhydrazone. Am I clear? Okay. Next one. I'm having carbonyl compound. It's treated with NH2, NHC double bond O NH2. What is Z here? This entire group is Z here, students. Slight amount of H plus. This is the intermediate. Delocalization, departure of OH, formation of carbazone. What you need to simply do, remove the both the hydrogen connected to nitrogen, and then you simply form the product as C doubly bond NZ. So the most important part of this reaction is identification of Z. Once you identify Z, you need to simply substitute Z. Here the Z is this one, right? The product formed is referred as semi-carbazone. This is carbazone. Now, if Z is OH, the product formed is oxime. If Z is NH2, that is NH2NH2. Carbonyl treated with hydrazine, the product formed is hydrazone. Carbonyl treated with phenylhydrazine, the product formed is phenylhydrazone. Carbonyl treated with 2,4-DNP, 2,4-dinitrophenylhydrazine. In that particular case, this is your product formed, and here we get solid precipitation. So basically it's a test of carbonyl compound also. Both aldehydes and ketones responds positively towards 2,4-DNP. What is 2,4-DNP? 2,4-dinitrophenylhydrazine. NH2. Here I am having this one NO2, 2 and 4. This is nothing but 2,4-DNP. This 2,4-DNP reacts with carbonyl and we will have a yellow precipitation of, or orange precipitation, generally we say it as yellow precipitation, of 2,4-dinitrophenylhydrazone, right? Next, semi-carbazide, the product formed is semi-carbazone, right student? Here it's NH2, NH, this group is Z. So I hope you understood this reaction, that is addition of carbonyl compounds to ammonia derivative, or we can say it addition of carbonyl to NH2Z. The product formed is C double bond NZ. Shall we move ahead? Let's move ahead. Next one. A very important name reaction referred as Beckmann's rearrangement. Let us try to understand this particular reaction also. I'm having oxime. How can we form oxime? If I treat any carbonyl compounds with hydroxylamine, R C double bond OH treated with NH2OH in the presence of HCl, the product formed is RC double bond NOH and H, and it's nothing but hydroxylamine. Now this hydroxylamine, whenever treated with any protic acid, undergo rearrangement reaction to form amides, and this particular reaction is a name reaction referred as Beckmann rearrangement. So from hydroxylamine, or from basically oximes, we get amide as the final product. I hope you understood it. Now let's discuss the mechanism of this reaction. Student, I'm having oxime. Now this oxime is treated with any protic acid. Protic acid is a source of H plus. What it will do? It will protonate alcoholic part. So this OH will get protonated. Now I will have the formation of H2O positive, right? Which will act as a very good leaving group. Now what will happen? We'll have internal attack. The group which is opposite to this OH2 will attack from the backside. The group will attack which is exactly opposite to OH group. So let us suppose this group is opposite to OH group, so it will attack from the backside. Then this will act as a very good leaving group, will get departed. As soon as the CR- bond is cleaving, I will have positive charge on carbon. I will have the formation of carbocation. On this carbocation, water will attack, right? I will have the formation of RCOHH doubly bonded NR. Oxygen cannot bear positive charge. It will readily undergo deprotonation. I will have the formation of RCOH doubly bonded NR. Now, sort of enol system, in all, imine, right? Okay, now this one will readily undergo tautomerization, and I will have the formation of amides. I will have the formation of amide. But student, always keep in mind, this reaction is highly stereospecific reaction. Only that alkyl group will migrate, which is exactly opposite to OH, or which is anti with respect to OH. Let us try to understand it. I'm having a compound C doubly bonded N OH lone pair. Here I'm having Me. Here I'm having ET. It's treated with H2SO4, or I can say simply H plus. How will you form the product? Let's write it one step by step. Student, first I will do the protonation. So I'm going to do the protonation. NOH positive ET, and here Me lone pair. Obviously this H2 is a very good leaving group. It will have a very high tendency to get departed. Now as soon as it departs, basically this methyl group will attack from the backside. It will undergo rearrangement. This CME bond will cleave. This Me will attack on nitrogen, and H2O will migrate. Here the migratory aptitude is stereospecific. It's not dependent on which is more nucleophilic or which is having a higher electron density. No, here only that alkyl is going to migrate which is anti with respect to OH. So now this methyl has migrated. I will have the formation of ET, P. Now loss of one bond, so it will get a positive charge, doubly bonded N, Me. Right? Now what I will do? Attack of water on this carbocation, formation of alcohol, ETCOH doubly bond Me. This one will readily undergo tautomerization, have the formation of ET C double bond O N H, or I can write it as H M E. Which type of amide we are getting here? 2-degree amide, secondary amide, right? Amide. I hope you understood this reaction. Oximes, whenever treated with H plus, undergo rearrangement and forms amides. This is how this reaction occurs. I hope you understood it. Please copy it, then we'll move ahead. And now we have one more reaction where we are going to do the same thing. And now this particular reaction we have studied in the previous chapter, hydrocarbons, right? Carbonyl compound, whenever treated with NH2NH2, that is nothing but hydrogen in alkaline medium, undergoes Wolff reduction, and we will have the formation of alkane. This carbonyl compound is reduced to alkane. Carbonyl treated with N2H4 in the presence of OH minus, remove oxygen, add to hydrogen, right? Okay, let's see how does this reaction occur. Student, this particular reaction mainly occurs in alkaline medium, OH minus. Let's see. I'm having a carbonyl compound, right? It's treated with NH2, NH2. We have studied this reaction just now, right? NH2Z. So I will have the formation of C double bond NZ. NH2. Carbonyl. Now student, this is treated with a base OH minus. What this base will do? It will snatch this acidic hydrogen. I will have the formation of C double bond N, NH negative, like this, right? A base, acidic hydrogen, acid base reaction, removal of water, formation of N negative. This N negative will delocalize. As soon as this one delocalizes, this pi bond will shift on the adjacent carbon, and I will have the formation of C negative N doubly bond N H. Right, students? Obviously, it is going to take H plus from water, and I will have H2O. So it's going to take H plus from water, and I will have C H N double bond N H, right? Now all I can take base, or even I can delocalize this one, right? As soon as this one delocalizes, nitrogen will have 3 bonds getting formed. This will act as a leaving group. This I will have the formation of N2. Now this particular, obviously, let's write it in one more step, H, and then, right, students, negative plus N2. In the next step, this C negative is going to take hydrogen from water, or from here also, this is also the acidic hydrogen. I will have the formation of HH and 2 alkyl group. So this is how this particular reaction occurs. This Wolff-Kissner reduction occurs in alkaline medium. Carbonyl treated with hydrogen in the alkaline condition, I will have the formation of alkane. Students, now let's practice some questions in order to understand this concept in a better way. First one, I'm having carbonyl compound, that is cyclohexanone, and it's treated with hydrogen in the presence of OH minus. Which reaction? WKR. Can you tell me the product? So easy. Simply remove this oxygen, add 2 hydrogen. The product formed is cyclohexane only. So a carbonyl compound, the keto compound, gets reduced to alkane, right? Let's move to the next one. I'm having a keto compound. At the same time, this compound is having Cl also. First, it will reduce this carbonylic carbon. Well, will the reaction stop here only? The answer is big no. Student, the medium is alkaline, so it will act as a base, and I am having a 2-degree alkyl halide. A 2-degree alkyl halides may undergo elimination reaction if treated with a base. So no doubt from here I will get alkane part, but this one will also undergo dehydrohalogenation. I will remove one hydrogen from here, Cl from here, and I will form alkene because the reaction is occurring in basic medium. Let's write that. So I will have phenyl alkane. This carbonylic carbon will get reduced to alkane, and now here I will have the formation of alkene. So dehydrohalogenation, removal of HCl. Right? Shall we move ahead? Let's move ahead, student. Now, once again, I am having a carbonylic carbon, but now the reagent is different. ZnHgHCl. Have we heard about this particular reagent? Yes. This nothing but Clementine reaction, right? So this particular reaction is referred as Clementine reduction. It is also used for the reduction of carbonyl compounds to alkane, but this reaction occurs in acidic medium. Acidic medium, right? Now in acidic medium, first this carbonylic carbon will get reduced to alkane. I will remove this doubly bonded O. I will add 2 hydrogen over there, and now on here this OH, since the reaction is occurring in acidic medium, it's a source of H plus. Can I say this alcohol will get protonated, and as soon as it gets protonated, it will get departed, and I will have the formation of carbocation. And on this carbocation, the nucleophile Cl minus will come, will approach and will attack over here, right? So I will have the formation of, or I will have the replacement of this OH by Cl. So the product formed is benzene ring, right? Here simple alkane, and here I will have chlorine. OH getting replaced by chlorine. Why? The reaction is occurring in acidic medium. Suppose if I have to retain this OH group, but I have to reduce this carbonylic carbon, I have to reduce this C double bond O. Which reagent I am going to use? Wolff-Kissner, because OH lone pair will act as a Lewis base. Here the reaction won't occur. Simply this one will get reduced. This OH will remain as it is. If I use Wolff-Kissner as a reagent, but if I use Clementine, this OH will get reduced or will get replaced by chlorine. Am I clear, students? Shall we move ahead? Let's move ahead. Student, let's discuss one more reaction, and it's also an application of nucleophilic addition reaction only. Now in this reaction, what I am going to do, I am going to take any carbonyl compound, aldehyde or ketone, any carbonyl compound. This carbonyl compound is treated with any per acid. Can you tell me a few per acid? Peracetic acid, perfluoric acid, PFA, peracetic acid, PAA. The formula is CH3, C double bond O, O, OH. This is nothing but peracetic acid. So I can take any per acid, acetic acid here. Okay. Now what this per acid will do? It will do the oxidation reaction of this carbonylic carbon, and my final product will be simply there will be insertion of one additional oxygen to this carbonylic carbon. So I can do what? I can have C double bond O, O, R and R dash. Student, now the product formed may be ketone ester or may be acid depending on the substrate. If I am taking aldehyde, in that particular case, my final product will be acid. Let me explain you. I'm having C double bond O, H and R. Is it an aldehyde? And now let us suppose it's treated with perfluoric acid, or it's treated with perfluoroacetic acid, CF3, C double bond O, 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 H, and heated. Okay. Can I say what I am going to do? I am going to remove this oxygen. Now where this oxygen will get added? It will get added to that side of carbonylic carbon which is having a better migratory aptitude. Now students, we have studied this hydride ion is having the maximum migratory aptitude in the rearrangement reaction, right? So this additional oxygen will get added to this right side of carbonylic carbon because hydride is having maximum migratory aptitude. Simply you need to insert oxygen on that side of carbonylic carbon which is having a better migratory aptitude. Hydride, phenyl, 3 degree and like that. Am I clear? Okay. So in this particular case, my product is going to be RC double bond O OH. So if it's aldehyde, we will get acid. If it's ketone, we will get ester. Student, let's practice few questions in order to understand this particular concept in a better way. I'm having benzodiazepine and it's treated with a per acid, and this per acid is metachloroperbenzoic acid, MCPBA. Okay, it's also a per acid. Can I say there's one more oxygen, students, here? Okay, can I say this additional oxygen will, I will remove this additional oxygen from here, and where it will get inserted? It will get inserted to that side of carbonyl which is having more migratory aptitude between hydrogen and phenyl. Which one is having better migratory aptitude? Hydrogen. So this additional oxygen will get added to hydrogen side of the carbonyl, and the product formed will be pH C double bond OH. Am I clear? Okay, let's move ahead. Now I'm having pH C double bond O Me treated with perfluoroacetic acid, PFA. One additional oxygen, right? CF3 C double bond OH. Can I say this oxygen is the additional oxygen? Now where this additional oxygen will get added? It will get added to that side which is having better migratory aptitude. Now between phenyl and alkyl, phenyl is having a better migratory aptitude. So this one will get added to phenyl side, and the product found will be pH O C double bond O Me. So what you need to do, if it's ketone, add oxygen to that side which is having a better migratory aptitude, right? In that case the product will be ester. In case of aldehyde, you always form acid. Am I clear? Okay, now you are having a cyclic ketone and treated with CH3 C double bond O18H. Now this O18H is given because maximum time we simply insert oxygen. But which oxygen? This is important. This additional oxygen we have to insert. This is the additional oxygen because it's a part of carboxylic acid, right? C double bond O and H. This is the additional oxygen, right? So now I am going to remove this additional oxygen and it will get added to that side of carbonyl which is having better. Now can you repeat it, because I have told this statement at least minimum 10 times, right? Which is having a better migratory aptitude. This oxygen will get added to this side. Why not left side? The reason is 3 degree alkyl is having a better migratory aptitude as compared to 2 degree or primary, right? So now I will have 6-member cyclic ring, right student? Here I will have the insertion of oxygen and this alkyl will come here. Let me write it in a better way. Right? And now this is the alkyl group. So this is my final product. So here the cyclic ketone is getting converted to a cyclic ester. Insertion of oxygen on that side, which is having a higher migration ability. Let's move ahead. Addition of NaHCO3 to carbonyl compound. Student, few carbonyl compounds, mainly aldehydes and only methylated carbonyl, reacts with this NaHCO3. It gives addition product like this. I am having R, C double bond O, H, and now if it's treated with NaHCO3, here it's an electrolyte Na plus HCO3 minus, so this hydrogen sulfide will do addition reaction with this, and I will have the formation of RCO negative H SO3H, right? And here I will have H. I can put one hydrogen over here also, right? Because obviously I will have water, so I will have OH. Now this reaction is highly reversible reaction, right? Maximum time it will be shifted in the backward direction because my nucleophile is a very bulky nucleophile. Second thing, this reaction is a highly specific reaction. It's also used sometimes as a test in order to separate aldehydes and ketones. With aldehydes, it will always react, but with ketones, it will react only with methylated ketones. It won't react with any other ketones. Am I clear? Only methylated ketones will give addition product with this nucleophile or will give addition product with sodium hydrogen sulfide. Now let's talk few more reactions on this carbonyl compound. Now let's talk some reduction reactions. Students have already studied this reaction. Whenever I am having a carbonyl compound and if I do catalytic hydrogenation, carbonyl compound treated with H2 in the presence of NiPDPT, this C double bond O will reduce and I will have the formation of alcohol as the product. So carbonyl compounds on catalytic hydrogenation, whether it is aldehyde or ketone, both of them will get reduced to H2 in the presence of NiPD or PT. Simply what you need to do, remove this double bond, add one hydrogen to oxygen and one hydrogen to the carbonylic carbon, right? If it's aldehyde, we will get primary alcohol. If it is ketone, we are going to get secondary alcohol. Right, students? I hope you understood this one. Please copy it. Students, now we have studied this one also. LiLH4 and NaBH4. Reduction of carbonyl compounds using lithium aluminohydrides and sodium borohydrides, right? We have studied this particular reaction. It's nothing but a source of H minus, right? So this H minus will get added to the carbonylic carbon. It will do nucleophilic addition reaction to the carbonylic carbon. As soon as this H minus attacks here, this bond will shift. I will have formation of O negative and this O negative will snatch H plus from solvent. So I will have the formation of RCH, OH and H. If I use metal hydrides, the H connected to this carbon is basically coming from either LiLH4 or NaBH4. The H connected to oxygen is coming from solvent, right? This one coming from either LiAlH4 or I can write it as SBH, that is sodium borohydrate NaBH4. Right, students? Please copy it. Students, now let's move ahead. Addition of Grignard reagent over carbonyl compounds. We studied this one also, right? Here Grignard R negative, MgBr positive. There is no acidic hydrogen, so this R negative will do nucleophilic addition reaction. This R negative attacks on the carbonylic carbon, the pi bond will shift. I will have the formation of C, let's suppose if it's aldehyde RH and the Grignard part is R dash O negative MgBr positive in the next step. It's treated with solvent H plus H2O. This O negative will snatch H plus from here and I will have the formation of RC R dash H OH. Right, students? We've studied these reactions, simply a revision. Shall we move ahead? Let's move ahead. Reaction of carbonyl compound with PCl5. This PCl5 acts as chlorinating reagent. What it will do, in case of alcohol, it was replacing OH, right? And this OH was getting substituted by chlorine. Here also, this C double bond O will get replaced by 2-chlorine. So simply I will have the formation of geminal dichloride. Whenever a carbonyl compound is treated with PCl5, we will have the formation of geminal dichloride. Along with that, we will have POCl3 getting formed as byproduct. Right? The most important is this one. Carbonyl compound, whether it is aldehyde or ketone, R dash. Both of them, if they are treated with PCl5, what this PCl5 will do, it will do chlorination of carbonylic carbon. Remove this oxygen and add 2-chlorine on the carbonylic carbon. So I will add 1-chlorine over here, 1-chlorine over here, and R dash over here. Geminal dihalide system. Please copy it. Students, till yet mainly we were studying the nucleophilic addition reaction on carbonylic carbon itself, right? But in case of carbonyl compound, apart from this carbonylic carbon, there is one more site where the reaction can occur, and that is alpha carbon. And in that case, if that alpha carbon is having any hydrogen, that hydrogen will be referred as alpha hydrogen. Now we have studied this alpha hydrogen is relatively acidic, right? So whenever this carbonyl compounds having alpha hydrogen is treated with base instead of nucleophilic reaction, the carbonylic compound will undergo acid base reaction, and the best example of that particular reaction is aldol reaction. Let us try to understand what do we mean by this reaction. Highly important reaction for all the competitive exam, whether it is JEE mains, NEET or advanced. Every time questions are directly asked from this particular concepts. So let's try to understand aldol condensation. Carbonyl compound having at least one alpha hydrogen, Can I say this carbonyl compound is having alpha carbon? This carbon is referred as alpha carbon, and alpha carbon containing hydrogen is referred as alpha hydrogen. So will this compound undergo acid base reaction? Definitely yes. If it's treated with either dilute acid H2SO4 I can take, or I can take dilute base. Generally you will get dilute base itself, OH minus. Carbonyl compounds, whenever treated with a dilute acid or base, undergo enolization to form a product beta hydroxycarbonyl, and this beta hydroxycarbonyl is referred as aldol. And now when this beta hydroxycarbonyl is heated strongly, it readily undergo dehydration. I will remove one water molecule from there and it will form alpha beta unsaturated carbonyl as the final product. Carbonyl compounds having at least one alpha hydrogen will readily undergo enolization to form a product that is referred as beta hydroxycarbonyl, and beta hydroxycarbonyl on heating undergo condensation, and the final product is alpha beta unsaturated carbonyl. Shall I write the reaction now? Yes, let's write it. Shall I write the product, students? Yes, let's write it. I'm having H, C double bond O. I'm going to remove one hydrogen from here, so CH2, then COH, then we will have H and then CH3. This particular product is referred as, this is alpha. Can I say this carbon as alpha carbon? And can I say this carbon as beta? On beta carbon, I'm having a hydroxyl group. This is beta hydroxy carbonyl. And beta hydroxy carbonyl is referred as aldol. And when this beta hydroxy carbonyl is heated strongly, it readily undergo dehydration or condensation. And what I am going to do, remove hydrogen from alpha carbon and OH from beta carbon, and form a double bond between alpha beta. Can I say this is alpha and this one is beta? So yeah, now the product which I am going to write is HC double bond O, C, H, one hydrogen I have removed from here, doubly bond C, OH I have removed from here, H and CS3. Can I say it's nothing but alpha beta unsaturated carbonyl, right? This particular reaction is referred as aldol reaction. Aldol reaction. Okay. How does this reaction occur? Let us try to understand that. Students, we have studied alpha carbon containing hydrogen is alpha hydrogen, and alpha hydrogen is always acidic in nature. So whenever it is treated with base, what the base will do? It will attack on this alpha hydrogen and will snatch one acidic hydrogen. So can I say, as soon as the base attacks over here, HCCH3 treated with dilute base OH minus, I will have acid base reaction occurring and I will have the formation of enolate ion, right? This one, this OH minus simply snatches one hydrogen from here and I will have the formation of enolate ion. This enolate ion will act as a nucleophile, and what it will do, the second step is nucleophilic addition reaction on the carbonylic carbon. So in the second step, this enolate ion will attack on the carbonylic carbon, CH3, C double bond OH. I will have AN reaction, right? And now the product is going to be H, C double bond O, CH2, right student? Then we will have C double bond O. Now here I will have OH, H, and here CH3. And it's nothing but beta hydroxy carbonyl, right? Now simply heat it. As soon as you heat it, remove H from alpha carbon, OH from beta carbon, and the product will be HC double bond O, CH double bond C, HCH3. Complex reaction occurring in two steps. I talk about this aldol reaction, and if I summarize it, can we simply remember it like this? First step, acid-base reaction, where a dilute base is attacking on alpha carbon having alpha hydrogen, right? We will have the formation of enolate ion. This enolate ion is a weaker nucleophile. Now what this weak nucleophile will do, it will do nucleophilic addition reaction on the carbonylic carbon, and I will have the formation of beta hydroxy carbonyl. This beta hydroxy carbonyl, on heating, undergo condensation. I am going to remove alpha hydrogen from the alpha carbon and OH from the beta carbon. So basically I will remove water molecule and I will form alpha beta unsaturated carbonyl. Student, this particular reaction is referred as self-aldol condensation. Why? If we'll see here, the first step is itself a reversible step. Why? You will say, sir, it's a acid-base reaction. No doubt it's a acid-base reaction. But here, the reacting species are weak acid and weak base. So the reaction is reversible. So obviously, all the moles of reactant won't get consumed. Some of them will get converted to enolate ion. And now this enolate ion will attack on the unreacted carbonyl. That's why this reaction is referred as self-aldol. Am I clear, student? If they give you 2 mole, it's okay. Even if they don't give you, you do self-aldol until unless they don't give other carbonyl. If only one type of carbonyl is given, the reaction is always self-aldol. Now the question is, do we need to write the mechanism always? Or do we have any shortcut to write the product? Yes, we have. Let's try to do it. Student, let us suppose I'm having a carbonyl compound like this, CH3 C double bond O CH3, and it's treated with dilute OH minus and heated strongly. Can you write the product? Can you write the product easily? Tell me. No? Okay. You do one thing. Write as it is, the underlined one. Okay. I'm going to write as it is, C double bond O. Now, from here, remove one hydrogen because that hydrogen is basically used in acid-base reaction. Okay. Now, perfect. Again, now write this carbonylic carbon. Carbonylic carbon I am writing, but now what I am going to do, I will write OH over here. This carbonylic carbon by attack of enolate ion is converted to OH. So I will write OH over here. And now I will simply repeat these two species, CH3 and CH3. If we look at this product, it's nothing but alpha, beta, hydroxycarbonyl. Okay, let's do one more. CH3, C double bond O, pH. Right? How will you do it? You're going to this is having alpha hydrogen. So you want to enolization on from this side. Am I clear? So simply repeat this one. Dilute OH minus. You need to simply write this pH C double bond O. Now what you need to do? Just write CH2. And now simply convert this one as OH, pH, CH3 and join this with CH2. So you will have C, OH, pH, CH3. I hope you understood this. In the second step, what I am doing, I am reducing this to alcohol and then I am keeping both the alkyl group as it is. I am attaching it to the alpha carbon. Now, if I have to form alpha beta unsaturated carbonyl, what I will do? I'll simply heat it. pH, C double bond O, CH, C, then we'll have pH, then we'll have CH3. This is alpha beta unsaturated carbonyl. Right, students? I hope you understood it. Please comment. Shall we move ahead? Yes. Now, you need to do both these questions. This one we have done right now, right? Okay, you can do it easily. Can you do it? Yes, you can do it. This is the alpha carbon. This is the alpha carbon. You can generate enolate from either side, but from only one side. Let me generate enolate from this side. So what I am going to do? I am going to write this one as it is. Perfect. And now this carbonyl as it is. Now from this side, once again, I will have enolate and this enolate will attack on this. So what I am going to do, right, students, here I will have O negative and this will get attached and O negative will get converted to OH. Now is it alpha beta unsaturated carbonyl? Alpha carbon, beta carbon. From alpha basically I have joined this alpha carbon to the carbonylic carbon of the other one, self one. right? Now I simply need to heat it. I will write double bond O. This is alpha beta unsaturated carbonyl. Formation of alpha beta unsaturated carbonyl is very easy. Formation of beta hydroxycarbonyl. What you need to do simply remove one alpha hydrogen. Now keep one of the carbonyl as it is. Just simply remove that one alpha hydrogen. And now join this alpha carbon with the carbonylic carbon, and that carbon should have alcohol now. Keep the alkyl group as it is. Am I clear? So this alpha carbon will now directly get connected to the carbonylic carbon of the next compound, and that carbonylic carbon, instead of having doubly bonded O, will now have OH. We will have beta hydroxy carbonyl, right? Okay, this one, it's nothing but pH C double bond O CH3. What I will do, I will remove one hydrogen from here. I will write pH C double bond O CH2. Now this is my alpha carbon. This alpha carbon will get connected to the carbonylic carbon. Now this carbonylic carbon will have OH, and alkyl group will remain as it is. Now this one on heating will give me, this is alpha, this one is beta. Remove H from alpha and OH from beta, and you will have pH C double bond O CH double bond C CH3 pH alpha beta unsaturated carbonyl, right? I hope you understood this one. So shall we move ahead? Let's move ahead. Now mainly we were talking about self-aldol condensation. Now it's time to discuss cross-aldol. What will happen in this particular case? Student, here I'm having two carbonyl compounds and both of them are having alpha hydrogen. Let's see. I can have CH3, C double bond O, H, and now it's treated with, let us suppose, CH3, CH2, C double bond OH. Right, students? And here, now both of them are treated with dilute base, that is dilute OH minus in the presence of H2O and heated strongly. Okay. So what will be the product? Student, in this particular case, we'll have mixture of products. I can do self-aldol of this one. Let's suppose if it is A, then if it is B, it can do aldol with A only, then B can do the self-aldol, and then we can have one cross-aldol also. So we'll be getting a mixture of products in this particular case. Let's try to do it. Student, if I generate enolate from here, and if I do the self-aldol of this one, can I say I will write the product as CH3, or let me write it like this in a better way. H C double bond O CH2, then I will write C OH H CH3, right? I hope you understood this one. This is the self-aldol of acetaldehydes. And if I'll do the condensation process, I will write the product as HC double bond O CH doubly bonded CH CH3. This is the self-aldol of this one. I can do self-aldol of this one also. Let me write that also. Let's write that. Now this one is really important. Can I say this carbon as the alpha carbon? Right, student? Okay. So I'm going to remove hydrogen from here. Now this particular carbon will have one deficiency of hydrogen, and this carbon will get added to the other carbonylic carbon, right? So how I will write? I will write C, one hydrogen, one CH3, right? One C double bond O. Am I clear? And now this carbonylic carbon is having hydrogen, and now this was my alpha carbon. I hope it is clear. This alpha carbon now will get joined to this one. Now I will have OH over here, H over here, CH2 over here, and CH3. I can remove H from here and OH from here, and then I will form the double bond like this one, CH3, C, C double bond O, H, doubly bonded, C, H, CH2, CH3. Two products. Now, two more product I can form. Can you tell me those products? Yes. I can generate enolate from here and I can attack over here. AB, and then we can form BA. I will generate enolate on B and will attack on A. Let's first of all form AB type. Okay, I am generating enolate from A and attacking on B. Let's see. Let's write the product AB. I'm going to write H. Okay, H, C double bond O, CH2. Now this will get attached to C double bond O. Now, sorry, I will have alcohol over here. Just a minute. OH over here, and then I will have H, CH2, CH3, right? So this was AB type. We can generate BA also, right? I can generate enolate from the B type and attack on A type. If I generate enolate from B type, so if I'm generating enolate from here, it's nothing but CH3, CH negative, C double bond OH. How I will write it? Let me write that. I'm going to write it like this. H, C double bond O. Perfect. Now this is connected to C, CH3, and I will write this H here. Am I clear? I have generated enolate, and now I am going to attack it on CH3, CH, C double bond OH. So here I am going to form OH. It's connected to H, connected to CH3. I am going to remove H from here, OH from here, and the product formed will be HC double bond O, CCH3, doubly bonded CH, CH3. Right? So AB, BA. How many product you got? AA, BB, AB, and BA. You got 4 products. Right, student? Okay, let's do some question in order to practice or in order to strengthen this particular concept. Let's do it. I'm having pH C double bond O pH and it's treated with pH C double bond O Me. Perfect. Students, whenever we are having cross aldol product, the major product we always write as the cross only. We don't write self as the major one. If I am given to write a single product, I will write cross product as the major product. So student, from here I am going to generate enolate. I will write it like this, pH C double bond O, CH2, and now it will attack on this carbon. So here I will have COH, right, pH and pH. What I will do now in the next step, I am going to do dehydration. Obviously remove H from here, H from here and OH from here, and form alpha beta unsaturated carbonyl, CH doubly bonded C, pH and pH. Is this clear? Let's do the next one. This one. No alpha hydrogen, no alpha H. So I will generate enolate from here and attack on here. Can I say this carbon and this carbon are the alpha carbon and both of them are having hydrogen? So I can generate enolate from either side. Let me assume I am generating enolate from here. Then this carbon ion will attack here and I will have the formation of pH, a 5-member cyclic ring, that is cyclopentanone, and it's getting connected like this, C, OH, H and H, which on heating will give me alpha beta unsaturated carbonyl, CH2. right? So this is the final product which we will get. I hope you understood it. So students, whenever you see two aldehydes, then in that particular case we'll have cross aldol condensation. In cross aldol condensation, if you have to write a single product, then write the major product as the cross one. Am I clear? Let's move ahead. Students, moving ahead, the next type of aldol reaction which we have to study is intramolecular aldol condensation. When does this reaction occur? Students, such type of reactions mainly occur in case of dicarbonyl compounds. Dicarbonyl compound. This intramolecular aldol condensation will be mainly observed in case of dicarbonyl compounds. Dicarbonyl compounds. So the compounds would have minimum of 2 C double bond O group present. Second point, it supports 5-member or 6-member cyclization. We'll try to understand this also. And the third point, here always check, please write it, always check reactivity of C double bond O and form enolate from other side. What do we mean by this statement? Basically, by this statement we mean if I'm having two carbonylic carbon, it may be possible one of the carbonylic carbon may be sterically hindered, may be less reactive. So from that side, I am going to generate enolate ion. And the carbonylic carbon which is more reactive, the enolate will attack on that carbonylic carbon. So first I will check which carbonylic carbon is more reactive, and then I will generate enolate from other side and will do nucleophilic addition reaction on the most reactive carbonylic carbon. Am I clear, students? Let us move ahead. Now let's try to understand this with one example. Is it a dicarbonyl compound? Yes. Is it having alpha carbon? Yes. Can I say for this carbonylic carbon, this is going to be my alpha carbon and this one is also my alpha carbon, right? Okay. Now, which carbonyl is more reactive? Here the reactivity of both the carbonyl is same. Same alkyl group, same hydrogen aldehyde group, right? So now what I will do? I will generate enolate from one side. So I have simply done the acid base reaction and now I am going to generate enolate ion. So let's assume I have generated enolate ion here. Now I will have C double bond OH. What will happen now? This enolate ion will attack on the other carbonylic carbon, right? To form a cyclic ring. How many member cyclic ring I will get? 1, 2, 3, 4, 5. Let me draw a 5-member cyclic ring. Okay. On carbon number 1, I'm having one aldehyde group. Perfect. I'll put one C double bond OH over here. 1, 2, 3, 4, 5. This is carbon number 5. Now, basically this carbon ion has attacked over here. So I will have the formation of alcohol over here. OH and 1H. Right, student? So this is my alpha beta hydroxycarbonyl. Once again, aldol only. Now, what I will do? I'll simply heat it to form my condensation product, and that is C double bond OH and a double bond over here, alpha beta unsaturated carbonyl. I hope you understood this intramolecular aldol condensation reaction. Shall we move ahead? Let's move ahead. But first of all, please copy it. Students, now we have one more type of reaction, and this particular reaction is also really important. Reaction name is Cannizzaro reaction. Carbonyl compounds having no alpha hydrogen, no alpha hydrogen, no alpha hydrogen. Whenever treated with a strong base, with a strong base, or I can say concentrated base having minimum 50% concentration. Okay. Carbonyl compound having no alpha hydrogen treated with strong base undergo oxidation and reduction to give two different products. And the reaction is referred as Cannizzaro reaction. Let us try to understand it. Can you tell me one carbonyl which don't have any alpha hydrogen? Yes, benzaldehyde. pH C double bond OH. Is it having alpha carbon? No, because I have told you the condition for alpha carbon. It should be sp3 hybridized. Here, although this carbon is a neighbor of sp2, but this carbon is also sp2 hybridized only. So no alpha hydrogen. No alpha hydrogen. Now, if it is treated with a strong base, OH minus, let's suppose I am taking KOH. Okay, concentration 50 to 80%. Then what happens? This particular benzaldehyde will undergo oxidation. What is the oxidized product of aldehyde? Acid. So I'm going to write acid, C double bond O, OH, plus it at the same time it will also undergo reduction. And what is the reduced product of aldehyde? Alcohol. So carbonyl compounds having no alpha hydrogen whenever treated with a strong base undergo oxidation and reduction. If the species is same, basically we can say undergo disproportionation reaction to form acid and alcohol. Although since the medium is alkaline, it will exist in this particular form. pH C double bond O, O negative. And if K positive, potassium salt of benzoic acid plus CH2OH, right? This reaction is referred as Cannizzaro reaction. How will you remember it? Simply check whether the carbonylic carbon is having alpha hydrogen or not. If there is no alpha hydrogen, condition number 2, check whether the base is dilute or strong. If it is a strong base, simply do disproportionation, oxidation and reduction. Am I clear, student? Now let us try to understand the mechanism of this reaction. Friends, now let us try to understand the mechanism of this particular reaction. I am having aldehyde with no alpha hydrogen. The best example can be formaldehyde, HC double bond OH. It's treated with a strong base, OH minus. There is no alpha hydrogen, so no acidic hydrogen. Can I say this OH minus will act as a nucleophile? I will have AN reaction. So I will have the formation of HC, O negative, OH and H. Right? Now students, basically I am having a dioxyanion sort of species. And it's highly unstable. So what it will do, this O negative will undergo delocalization and then this RH will depart. So I will have hydride transfer. Although this process is really tough, right? Hydrogen is not a good leaving group. So it will have a very less tendency to leave in the form of H minus. But here it does not have any other option. This O negative will delocalize and the CH bond will cleave and it will get released in the form of H minus. Now what this H minus will do, since the reaction is highly reversible, it will attack on the unreacted part of formaldehyde. So can I say this H minus will once again do nucleophilic addition with this one, formaldehyde itself, and here I will have the formation of H, C, O negative, H and H, which on treatment with water or H3O plus, or I can simply write water, will give me CH3OH, right? Here, what will be the product? This O negative has delocalized, so I will have HC double bond O OH. Since the medium is alkaline, it will exist in the form of HC double bond O minus Na plus or K plus, depending on the base, right? Now, student, this reaction is also two-step process. Now here, the migration of hydride ion is nothing but RDS for this reaction. That will be the very slow step. Removal of H minus and attack of this H minus on unreacted carbonyl, unreacted formaldehyde. This formaldehyde here is getting oxidized as well as reduced. This is the reduced product. This one is nothing but the oxidized product. So formaldehydes or carbonyl compounds having no alpha hydrogen on reaction with OH minus undergo oxidation and reduction, and this particular reaction is referred as Cannizzaro reaction. Shall we move ahead? Let's move ahead. Student, I am having benzaldehyde treated with OH minus. We have done this reaction just now only. What will be the product? This one will get oxidized. The oxidized product will be pH C double bond O OH. Since the medium is alkaline, I will write this pH C double bond O negative plus pH. Reduced product is going to be alcohol. Now, student, here we have some isotopic effect. Let's see. Can I say in the first step, basically I was having formation of pH C double bond O negative, and here OD and D, right? So obviously this D minus will depart, student. Am I clear? As soon as this one attacks, this D minus will depart. Now what this D minus will do? This D minus will attack on this one. So now I will have the formation of pH. This one C, one D is already there, one D has attacked, and here I will have O and OD minus. So basically my solvent is D2O. So I will have D2O, CDDOD, and here I will have pH C doubly bonded O, D and OD. Right? This is the oxidized product. This is the reduced product. So sometimes the question may be asked on this isotopic effects also. Let's do two more questions in order to understand this concept. I'm having HC double bond OD treated with OH minus slash H2O. So the solvent is H2O here, source of H plus. Student, as soon as this OH minus will attack, I will have the formation of HC O negative D OH. Now which bond you will cleave? CH bond or CD bond? The one which is weaker. Obviously CH bond, it's much more weaker. So can I say H minus will get released and this H minus will attack now? So I will have H, C, H getting added, O negative, solvent water, so OH and D. Am I clear now? Simply write the dioxyanion, then check which bond is weaker, remove that one and attack on unreacted carbonyl. Is that clear? Okay. One more. I'm having HC double bond O D, OD minus. Let's write the dioxyanion. O negative, D, OD. Now which bond is weaker? H bond is weaker, CH bond is weaker. This one will cleave in the form of H minus, will attack over here. So what I will do, I will add O negative, H and D. Now this solvent is OD minus. So it's a source of D2O, D plus. So here I will have OD. Now I am giving you a shortcut through which you can do this solvent type question in less than 30 seconds. Okay. Let's see. You're having formaldehyde, right? HC double bond O and let's suppose D is there. It's treated with OH minus. You have to write the oxidized product. What you need to do? Simply add OH on the carbonylic carbon. This will be your final product. You can remove H or you can write it like this also. Now you have to focus on the reduced product. While writing the reduced product, what you need to do? Just take this hydrogen. So add one hydrogen to carbon, keep as it is, and this one will get reduced. Now, depending on the nature of solvent, if the solvent is water, add hydrogen to oxygen. If solvent is D2O, add D2 oxygen. Am I clear? This is how you can write the product. Am I clear, student? Okay, let's see. I'm having HC double bond OD, OH minus. In the oxidized product, I will simply add OH. This is my oxidized product. In the reduced product, what I will do, I will add hydrogen to carbon, and solvent is water, so I will add hydrogen to oxygen also. Add one hydrogen to carbon, one hydrogen to oxygen. Here, HC double bond OD treated with OD minus. What I will do in the oxidized product, I will add OD to the oxidized product as it is. Now, in the reduction product, what I need to do, I will add one hydrogen to carbon. Solvent is D2O, so I will add D to oxygen. Am I clear? Okay, let's move ahead. Compare the rate of hydride transfer. Students, we have studied that after the formation of dioxyanion, in the second step, basically that CH bond cleaves and hydrogen has to depart, right? Now the departure of or the rate of hydride transfer mainly depends on the electron density on the carbon. Higher the electron density on the carbon, better will be the rate of hydride transfer. So more the nucleophilic character on that particular carbon containing 2O, then higher will be the rate of hydride transfer. So whenever the question is asked related to the rate of hydride transfer, simply check whether the groups are electron donating groups or not. If it's an electron donating group, the rate of hydride transfer will be more. In this particular case, I am having plus M group. In this particular case, I am having a minus M group, in which case I will have more nucleophilic character or more electron density on the carbon containing 2 oxygen, the one where a plus M group is there. So the hydride transfer rate will be like this. Am I clear? Let's move ahead, students. Crossed Cannizzaro reaction. Student, till yet mainly we were doing self Cannizzaro. Just like self aldol, we were doing self Cannizzaro. Now we may have two different aldehydes or two different ketones with no alpha hydrogen. Then one of them will get oxidized and the other will get reduced. Let's try to understand it. I'm having PHC double bond OH, benzodiazepine, and now it is treated with formaldehyde in the presence of a base OH minus. Can you tell me which one will get oxidized and which one will get reduced? Student, always remember that carbonyl will get reduced, which is less reactive. Or in simple word, I can say that carbonyl will get oxidized, which is more reactive. Now between benzodiazepine and formaldehyde, can I say this is more reactive for addition reaction? So this one will get oxidized, right? So I will have HC double bond O, OH, acid base reaction. I will have HC double bond O, O minus. This one will get reduced. Why it will get reduced? In case of cross Cannizzaro, whenever I am having two carbonyls with no alpha hydrogen, the one which is more reactive gets oxidized, the one which is less reactive gets reduced. So this one will get reduced and my reduced product will be PH, COH, H and H. Right? I hope you understood this one also. Please copy it. Intramolecular Cannizzaro. Okay, let's do one question related to this intramolecular also. Student, I'm having C double bond OH, C double bond OH, right? Here, what I am doing, let me take this one, and here at this para position, I am attaching a nitro group. Meta with respect to this one and para with respect to this one. And now it's treated with KOH, 50% concentration, and heated. Can you tell me the product? Can you tell me the product? Here I'm having a dicarbonyl compound, just like intramolecular aldol. Here I'm having intramolecular Cannizzaro. The difference is here there is no alpha hydrogen. In case of intramolecular Cannizzaro, just like cross Cannizzaro, one of the carbonylic carbon will get oxidized and the other one will get reduced. Which one will get oxidized? The one which is more reactive. How do you check the reactivity of carbonyl? If an electron withdrawing group is connected to the carbonyl, if I am having a minus M effect acting on the carbonyl, in that particular case, the reactivity of carbonyl will be more, and that if the reactivity of carbonyl is more, it will simply get oxidized and the other one will get reduced. Now, can you tell me which is more reactive here? Which is more reactive? This one or this one? If I look at this particular aldehyde, exactly at para position, I am having NO2. So can I say here minus M is operative? Whereas if I look at this particular aldehyde, no doubt NO2 is there, but it's at meta position. So for this aldehyde group, minus I, for this one, minus M is operative. Where the electron deficiency is more? Here, right? So where OH minus will attack more easily? Here. So which one will get oxidized? The top one. Let me write that. NO2, C double bond O, O negative, and this one will get reduced as OH, CH2. Or I can write CH and H. Right, student? I hope you understood this one. First, I have formed acid. Since the medium is alkaline, acid-base reactions, I will have potassium salt of carboxylic acid. I hope this intramolecular Cannizzaro reaction is also crystal clear to you all. Moving to the next reaction which we have to study is Wittig reaction. This particular reaction is mainly used for the synthesis of alkene from carbonyl compound. Carbonyl compound, whenever treated with phosphonium halide ion, PHOSPHONIUM, halide ion, this particular carbonyl will undergo 4-member cyclic transition state. It is referred as betaine. In this cyclic transition state, finally I will have the formation of alkene. We see this as 2+2 cycloaddition. Now I am giving you a shortcut how to do this. Student, either you will see the reagent as C negative P positive PH3, or you may see it like this: C doubly bonded P, PH, PH and PH. Here you are having alkyl group. What you need to do? What you have to do? Remove this carbonylic oxygen, remove this entire thing, take this one and join it with carbonylic carbon via a double bond. Am I clear? Simply take this alkyl part, join it with carbonylic carbon via a double bond. Remove this oxygen. Your product is going to be alkene. Okay. Let's do one question related to this one. Student, I am having a cyclocarbonyl, cyclohexanone, right? Cyclohexanone. And this one is treated with halide ion. What I need to do? I am going to remove this one. Okay. I will take this part and I will attach it to this carbonylic carbon via double bond. So can I say my product will be doubly bonded CH, CH2, CH3. Apart from this, this oxygen will get connected to phosphorus. So I will have P double bond O, PH, PH and PH. Am I clear? Is this concept clear, everyone? Shall we move ahead? Let's move ahead. Student, now it's time to discuss some important tests, and these particular tests are definitely asked in almost all the competitive exam once again. the test which we are going to discuss. First, we will be talking about haloform reaction. Then we'll discuss tolerance and Felling's test. All the Felling's test we had discussed in the previous classes also. So mainly my entire focus will be on two main important tests. One is tolerance test and the other one is haloform reaction. I'll start this one with haloform. Let's start. Haloform reaction. Highly important once again. Haloform reaction. Basically, whenever I am having a methylated carbonyl means on one side of the carbonyl, there should be one methyl group. It's mandatory for this particular test. If a compound has to respond positively towards haloform test, then this presence of methyl group is mandatory. Now, a methylated carbonyl, whenever treated with X2 in the presence of OH minus, basically it undergo oxidation reaction. I will have the formation of R, C, double bond O, O negative. Along with that, I will have the formation of CHX3, and this particular CHX3 is referred as haloform. So will all carbonyl respond positively towards this haloform? The answer is big no. Only methylated carbonyl. Okay, only methylated carbonyl will respond positively towards this haloform reaction. Am I clear, student? Right now, I am not going to discuss the mechanism of this. Simply, I will enlist all those compounds which may give positive haloform test. Let's write one by one. Let's start from alcohol itself. Among alcohol, which one will give haloform test positively? If I talk about primary alcohol, student, CH3CH2OH. This one, whenever treated with X2 in the presence of OH minus, it will respond positively towards haloform. Why? Because this X2 and OH minus is a mild oxidizer. So this ethanol will get oxidized to CH3, C double bond OH. Acetaldehyde. Now I am having a methylated carbonyl, will easily respond positive haloform test, right? So among primary alcohol only ethanol will give, or ethanol shows positive haloform test. Among secondary alcohol, if I am having a structure like this, CH3, COH, R dash. Now this R can be anything, but one side I should have this CH3 group. And now if it's treated with X2 in the presence of OH minus, it will easily undergo oxidation. First, I will have the formation of methylated carbonyl, and now this methylated carbonyl will give positive haloform test, right? If it's treated with iodine in the presence of OH minus, I will have my product as CHI3 plus RC double bond O negative R dash. Am I clear? So among alcohol, in case of primary alcohol, only ethanol. In case of secondary alcohol, if I'm having a structure CH3OH R dash, then such secondary alcohol will respond positively towards haloform test. Tertiary alcohol won't give positive haloform test. Am I clear? Now, next one. Among carbonyl compounds, if I talk about aldehyde, only this one will respond positively towards haloform. If I treat it with I2 in the presence of OH minus, the product which I am going to write is CHI3 yellow precipitate plus HC double bond O minus. This part will get oxidized. This one will get converted to haloform. If it's iodine, iodoform. If it's chlorine, chloroform. Am I clear? Okay. Now among ketone, only methylated ketone, CH3 C double bond O R dash, methylated ketone. I2/OH minus will give or will respond positively towards iodoform right now. plus R dash C double bond O, O minus. Okay. Now, students, let's discuss about few more compounds which will respond positively towards haloform test. Let's discuss it. We have discussed till ketone. Okay, carbonyl. Student, if I'm having a dicarbonyl compound, mainly beta dicarbonyl compound, that will also respond positively towards haloform. Let's see. I'm having a compound like this. Okay, this one and this one. And now if it's treated with I2 in the presence of OH minus, even this particular compound will also respond positively towards haloform. Can you tell me the product? What you need to do from here, you need to form haloform. This is the active methylene group, highly acidic, right? So from here, I will snatch CHI3 from this carbon. Now the ring will break. This one will also get oxidized, right? So can I write it like this now? Plus double bond O, O negative, and double bond O, O negative. So in case of beta dicarbonyl compounds, if I'm having CH2, or basically we can say all the beta dicarbonyl compounds will respond positively towards haloform tests. Am I clear, students? Let us move ahead. If I talk about acid derivative, will they give positive haloform test? Let's have a look. I'm having a compound like this, CH3C double bond O, OH. And now it's treated with I2 in the presence of OH minus. You can say, sir, here I am having a methylated carbonyl, so it should give. No. Student, if I am having a compound having the general formulas CH3C double bond O, G, and if this G is having lone pair and this lone pair is in resonance with C double bond O, even though it is a methylated carbonyl, it will not respond positively towards haloform test. Am I clear? So if this G is NH2, if this G is OR, if this G is X, if this G is OC double bond O, R, in all such case, even though on the left side I am having a methyl group, this one will not respond positively towards haloform test. I hope I am crystal clear. Right, student? Let us move ahead. Student, now it's time to discuss one more important test of carbonyl, and that is tolerance test. Tolerance test. Basically, this particular test is mainly given by aldehydes. But will only aldehyde respond positively towards tolerance test? No. First of all, you may ask, sir, what is tolerance reagent? Student, if I talk about this particular reagent, it's nothing but ammoniacal silver nitrate solution, AgNH3 2 plus OH minus. This is tolerance reagent. Tolerance reagent. So basically, if I talk about this tolerance reaction, it's also oxidation reaction in alkaline medium. Tolerance reagent. Okay. The second point, it's an oxidation reaction. Oxidation reaction occurs mainly in case of alkaline condition. Oxidation reaction in alkaline condition. It's a mild oxidizer. Mild oxidizer. Now, I'm going to give you a list of compound which will respond positively towards tolerance test. Okay, let's try to understand. First one, among hydrocarbon. If I talk about hydrocarbon, terminal alkyne, RC triple bond CH, if treated with tolerance TR, I will have silver mirror precipitation of Ag. This precipitation of Ag confirms the reactant or the substrate responds positively towards tolerance reagent. If a substrate is treated with tolerance reagent and if I get a silver mirror precipitation on the neck of the test tube, if I'm having some shiny layer getting formed on the test tube, it confirms the substrate has reacted with tolerance reagent and it is responding positively towards tolerance reagent. Okay, so first terminal alkyne, then among aldehydes, all aliphatic aldehydes as well as aromatic aldehydes. This one will also give. Second one, third one, pH C double bond OH will respond positively towards tolerance test. Definitely. Fourth one, among ketone, only one type of ketone will respond positively towards tolerance test, and that is alpha hydroxy ketone, referred as benzoin. Alpha hydroxy ketone, C double bond O and dash H. This one will also respond positively towards tolerance test. Hence, we have few more species which will respond positively towards tolerance test. Apart from this aldehyde, alpha hydroxy ketone, there are few more species which will give positive tolerance test. We have enlisted these compounds which are responding positive, but we have few more compounds. Can you name them? Yes. The first one, in this class only we have studied about this compound RCOHOR and H. Hemiacetal, highly unstable. Whenever treated with ammoniacal silver nitrate solution AgNH32 plus OH minus, I will have the formation of this Ag precipitate. Okay. Second, next one, formic acid. This one will also get oxidized by tolerance reagent and I will have Ag precipitation. This one will get oxidized to CO2. Next, I will have glucose. This one will also respond positively towards tolerance test. In all these compounds, how many compounds I have listed? 1, 2, 3, 4, 5, 6, 7. Right? We have many more compounds. All such compounds will respond positively towards tolerance test. But these are really important compounds. In your exam, questions won't come out of these compounds. If you remember this, and if the question comes on tolerance reaction, you can easily do it. Am I clear? Now, we have one more reaction or one more test, that is Felling's test. Students, so that's all about tolerance reaction. I'm having a few compounds. When these compounds are treated with ammoniacal silver nitrate solution, we'll get silver mirror precipitation. Tolerance reaction is an oxidation reaction in alkaline medium, right? Finally, you will get a silver mirror precipitate, right? Now, if a question comes on tolerance reaction, it can be asked like this, or it can be framed like this. Which of the following will give positive, or which of the following will respond positively towards tolerance test? One, or one more way, which of the following compounds will give silver mirror precipitate? They will give you one of the compound among the 7 one, and you have to simply pick that one. You have to simply remember these 7 compounds. Am I clear, students? Let's move ahead. Students, now we have one more important test, and that is Felling's test. It's mainly given positively by aliphatic aldehyde. Felling's test given positively by aliphatic aldehydes only. Aromatic aldehyde does not respond positively towards Felling's solution. Okay, in this particular test, basically we will have Cu plus 2, and this Cu plus 2 will get reduced to Cu plus 1, that is Cu2O. We'll get a red precipitation of this Cu2O. Whenever aliphatic aldehyde is treated with Felling's solution, we'll have red precipitation of this Cu2O. Cu plus 2 will get reduced to Cu plus 1, and this aldehyde part will get oxidized. Okay, I hope I am crystal clear. Friends, that's all about today's lecture. I hope you thoroughly enjoyed this. If you have any doubt, please do mention in the comment box. I'll be very happy to answer all your queries. Students, because of time constraints, we could not do more questions related to carbonyl compounds, but don't worry, we'll have a separate session where we'll doing lot of questions on carbonyl compound. Either it will be a simple question answer session or it will be a Menti session. Till then, give your best, and if you have any doubt, please do mention in the comment box. I thank you all for watching the lecture.